as 3 people walk in. Okay, we're getting started. I'm Bob Hancock. This is Optimizing Performance with Parallelism and Concurrency. And subtitle might be Not Optimizing with Parallelism and Concurrency, because we'll see that there are some cases that parallelism and concurrency are not always your best choice. And I have a friend who works for a major bank in New York, and he has a boss who says when things are slow, parallelize it. And that will not always cure your problems. So, just a little bit about me. I've been programming, 20 years now. Python was the 18th language that I learned. I get interested in something is there anyone else here other than me who's actually programmed in Eiffel? Oh, well, Doug, yeah. Okay. So, let's start off. These are the resources that we're using for this. Python 2.7, stackless 2.7.2, PyPy 1.7, which is the latest release, Python 3.2.2, Gevent, I'm using a beta version of it, of 1.0 B1, and this uses the new libraries, moved from libevent to libev, and we'll talk about why that's significant later. And file names will be indicated on the slides. I also have a bibliography, which is part of the packet, which has a huge amount of references that I've found over the last year that have to deal with all of this, and several books, about 9 of them, which I would say are essential reading if you have any interest in this. Testbed, Ubuntu, and my laptop, which is a 201, 8 gig of memory, 4 processors, and your average SATA drive. Now, the premise of this talk is that to make an informed decision, you've really got to understand what's going on under the hood. Because particularly when we talk about parallelism, concurrency, people have a favorite. It's a little bit like the religion of having a favorite language. I like this one. I like that one. But do you know what it does, and why do you think it's good? Also, when something new comes out, how do you evaluate it without running a POC or a bunch of tests? If you understand what it's doing underneath, because Python, one of the great things is it allows you to work on the problem, but it's a very high level of abstraction. And some of this will take a while to really sink into your head. And this is one of my favorite quotes from Guy Steele. They asked him, what is the most important quality that a programmer can have? And he replied, patience. So really take the time to understand what's going on. So here's a high-level overview of what we're going to go through. Come on, take a seat. Just find an empty space. Do we have enough seats? Yeah, there are 2 up here, 2 over here. So this is all going to be geared towards POSIX. I'm sorry for the Windows people here, but Windows does so many things in a different way that it would be an entirely different talk. We're going to talk about generators, coroutines, futures, which is one of the coolest things that they put into Python 3, the details of blocking and non-blocking I/O, Greenlets, libev, Gevent. Why do you care about this low-level stuff? Design considerations when you're putting something together. So before you even start writing any code, you can make an intelligent design. And what are the other options if you just can't get Python in the environment to do what it does? So let's agree on vocabulary first. Concurrency and parallelism are words that are thrown around almost interchangeably. Now, concurrency is when you have multiple things going in parallel that may need to communicate with each other. If you have a GUI and you have keyboard input, you have mouse input, you may have visual import, you may have pen import, other things which are running at the same time need to know that an event occurred, and what do I do? Parallelism is about taking deterministic processes that don't need to communicate with each other and shoving them down parallel pipes so you can get as much going as soon as possible. And a perfect example of that is the MapReduce, which is used a lot in Google. So, how does the operating system service requests? This may be a review of some of you from like your junior CS courses. First is, what is the OS? It's just a set of programs that manages the hardware and provides services for you. That being said, it's a very complicated program. And the kernel is the core of the program. You can download the kernel for Linux yourself at kernel.org. And you can make changes to the kernel and have your own kernel. Google does that. They have their own kernel so that when they read from a disk, their blocking size for reading from a disk is 64 megabytes at a time. So you can imagine what that does for throughput. Your applications talk to the kernel, say, listen, I want this done. I want to read. I want you to do something else, and I want you to give me the answer to it. So it's the person to whom you ask questions to get a response, And the important part about the kernel is that it is the only part of the operating system that can execute privileged instructions. Now, privileged instructions are generally when you're going to access a physical device like a network. Well, a network socket is the logical implementation of a port that you have out to the internet, which would be your Ethernet cable. It could be a disk device. It could be a database. You can't access those directly. Only the kernel can go to the devices, because you'll see once you've put the board together, do I use a DMA? Do I have this sort of bus, etc.? Now, kernel mode is where the kernel executes the operating level system instructions. And it operates only in protected mode, meaning that I know I'm the kernel and I know that someone else isn't coming in, it isn't a rogue program. And that's relatively only about recent, I'm saying, because it's only about 40 years old. And when the OS is in kernel mode, your programs must wait. Now, the word wait has a specific meaning when you're programming in C, where you wait for an event to occur or a conditional object to change. Wait, in this context, means the same thing as blocking. It means that your program has made a request of the kernel. The kernel cannot supply the answer immediately, so your system, your program has to sit there and wait. In fact, it blocks further execution until it receives a response from the kernel. This is what we mean when we start talking about blocking and non-blocking I/O. Oh, and the kernel talks via interrupts, hardware interrupts, which all have a number, to the physical devices. And the other mode is user mode, which is what you guys are doing. You're writing stuff that runs in user mode. It's where your code executes, and it talks to the kernel. It asks the kernel for a privileged instruction, and it gives you a result. Get me 500 megabytes from the disk. It goes out and does it. That's all you need to know about for now. And requests are in the form of a system call, which are referred to as traps. So interrupts are the hardware interrupts, which actually talk to the devices, and the system calls are traps. When the user space and the kernel is free to service other requests. So you've sent it off. It has to go out to a disk. Maybe it hasn't gotten it back from the disk yet, so the kernel's going to go on and do something else and only get back to you eventually. Now, the reason we talk about these two modes is long ago in the 1960s, there was only kernel space. That was it. You wrote a program that executed a sequence of events. If you screwed up, you didn't just crash your program, you crashed the entire operating system. So, about 1967, Bell Labs, GE, and MIT got together. And they said, well, everybody seems to have their own operating system. If you bought an IBM system, you had to buy their operating system. Let's create an operating system that will run on more than one machine. It was called Multix. I always have to read what it means. The Multiplexed Information Computing System. And also part of the impetus for this was the IBM 360, which is one of those machines that you'll see in the 1960s movies that filled up an entire room and had tapes running in both directions. They came up with the concept, what if we put a physical register on the chip, just a binary, that will say, I'm either in kernel mode or in user mode. And then the guy who's writing probably assembly code or Fortran at that point can't crash the entire system. And this was revolutionary, and this is where the guys at AT&T and Bell Labs went forward and said, we should write our own. And it's a project that died relatively quickly. Because has anybody ever heard of the principle, I forget the name of the book that's in, called Worse is Better? That's a principle and acceptance of things in computer science, that sometimes the absolute best is not accepted because something is easier to use or is more readily available, and the community adopts that. Many people felt that way about C. So this is why Bell Labs, who very much had that mentality, pulled out of the project. So Ken Thompson was sitting around bored. He was actually writing a game in assembly where you could have a spaceship go around to different planets. And it didn't run very well, and it was a PDP-7. So he said, you know, with the operating systems we're using, it doesn't work very well. And it was an old one that only had just the one mode in it. So he wrote a scaled-down version of Multix himself in his spare time. He wrote an operating system in assembly. And Brian Kernighan came by and made the joke that it was a uniplex system, hence the name UNIX. So as he started to do more with it, it was kind of ticking off management, because each time he played this game, in $1969, it cost them $75 of computing time to play a game. So a PDP-11 which was the first VAX that came out that had protected mode and it was lying around. So they said, why don't we write the operating system so it runs on this? Which gives you an idea of the way these guys thought. Why don't we write an operating system? You know what? The language I've been working on, BCPL, isn't really good. Well, why don't we change it? Okay, I've got some spare time. I'm going to change this and write another language so that we can write another operating system. And that's how C in Unix came about, which is very different from someone who says, I've got a new website and I want to get backing from it. It's a completely different mindset. So this is a trivia question. In the Unix password file, there's a field called geckos. And that's where you put the user's name, their telephone extension, what department they work on. Where does that come from? Okay. Stands for General Electric Comprehensive Operating System. At the time, the people that make our light bulbs were one of the major vendors of operating systems. And nobody remembers them now except for the geckos. And it was so prevalent that Bell Labs used it for their printing and all their other services, so that when they started writing this operating system, it was so prevalent they had to put information about the other systems in the password file, like the user's ID, etc. So when you put a new person on Linux now and you have to fill in the geckos field, you're filling it in from long ago when General Electric was a major vendor of operating systems. So, back to the technical part. Now, two words we're going to talk about. First one, or phrases, mode switch. That means now that there are two modes, you can be in either kernel mode or you can be in user mode. And when you switch between them, it's a mode switch. And moving from one to the other can have associated costs which aren't that huge. Okay? The big one, so let's take a look at what will happen here. If you're in user space and your process is executing and it makes a call to the system saying, get me 600 megabytes from the disk. What it has to do is it says, okay, the operating system on its scheduler receives, there's a trap from this program. Well, the first thing I have to do is, this guy is now at the top of the queue, so I have to service his request. I have to set my mode bit to 0 to say that I am now going to be in kernel mode. And while I'm in kernel mode, I can't do anything else. I execute the system call, I put the results in a buffer, I send it back, and then set the mode bit back to 1, saying that I'm ready to accept other things from user mode. This happens tens of thousands of times per second. Now, the context switch is slightly different. The context switch of the process, this is the technical definition. It's the union of user level, register level, and system level context. Because for each process that you have running, there are 3 parts which are maintained. The one, do we call it here user level? The user level is where your code is, sometimes called the text mode. If you have certain versions, Linux doesn't do it, but certain other POSIX, you can set the sticky bit on a file. And what that will say is, do not cache the text or user part of this file. You frequently do that for swap files, where you don't want it to be cached. But what we're saying is there are 3 things now. I'm going to do a context switch, so I have to take these 3 components. I have to copy them. So it's a mem copy of each one of those 3 components. I have to figure out where they're saved. I have to figure out what the virtual address is that I'm going to come back to, and I have to move it to a place that's going to be extremely safe. So here are the 4 steps. Decide whether to do a context switch, save the old process, and then once I have done that, I have to go back to the operating system scheduler and say, what's the next person up to do this? This is one of the most expensive operations that you can do on a system level, apart from like disk, seek IO, which are external devices. And this is one of the major limiting factors when you're running a parallel or concurrent program. So, what do things cost in general in a system? We'll look at the non-blocking operations, because blocking operations tend to cost a little bit less. As I said, I'm going out getting something for the disk, but I haven't got it back, so I'm going to go over here and do something else, and when it's ready, I'll send it back to you. So, reading a CPU register, it's basically the equivalent of having a thought in your head. Bang. It's there immediately. If you're reading main memory, you turn around to your file drawer, you pull something out, assuming you've got a good filing system. Now, the context switch is the equivalent of making an inventory of everything in your cube and its position relative to everything else. You move out of your cube, you move in your colleague who sets up the cube for himself, he works, makes an inventory of everything in your cube and its position relative to everything else, moves out, you move back, replace everything, and continue to work. That is the equivalent of what a context switch is going to be for your system. Now, for the blocking operations, a disk seek is like requesting a physical file from the branch office. You assume since it's part of the same company, it'll probably be a decent response, but you don't know if that person's out sick that day, if it has to go into a queue. But you can continue working while you're waiting for that to arrive. You go on to something else. Now, the network request, that has the greatest latency, because you never know where you're going out for a network request. If it's in the guy in the cube next to you, maybe he throws the paper over the cube. But as far as you know, it could be somewhere else. So maybe the guy in the next cube gets the response by somebody going from Japan, coming around and asking him if he has it and taking a return trip through Frankfurt. So that's where you're going to get the biggest blocking operations. And keep this in the back of your mind. If you're blocking, you can really take advantage of parallel processing. The non-blocking ones are less likely to help you. Now, we've been talking about this, but I want to drive the point home. The OS only executes one operation at a time. That's it. And by the OS, I mean the kernel. What if you have 4 cores? We say, well, I've got stuff executing there. The modern kernel, I think it's 2.6 and above, in Linux, they started fragmenting the kernel as opposed to having it loaded into one place. So there are certain parts that can be shared by individual processes, but eventually it all has to come back to the system scheduler to say who's next, who's in the queue. So no matter how quickly you do things, your operating system is still executing only one thing at a time. So what is multiprocessing if you're actually only doing very rapid sequential execution? Let's talk about what a process is first. Process is simply an instance of a computer program that's executing. That's easy. And you usually use the fork command for those of you who use C or have written at system level. And in Linux, it's slightly different. When you use fork, you're actually calling clone. And we'll see a picture of what that does later. And each process is given a unique ID in the system. And the ID is unique while the process is running. The process IDs get up, I forget what the level is now, but at one point they'll start reusing them. So apart from process 0, 1, and 2, which are reserved numbers, if you have a process that's running now and it's 793, that could be reused in the next couple of minutes if it's gone out and you have a lot of processes that are being created. So a thread exists inside of a process. Think of it as being subservient. You have this big silo, and then you have a bunch of little things which are stacked inside it. Those are the threads. What the thread does is it shares memory space with its parent. Okay? And threads are multiplexed within a process. And we'll see why that's important a little later on. Don't confuse them with the word you'll see in a lot of books, thread of execution. That's an unfortunate choice of terms. A thread of execution refers to the process that is executing at the moment, which isn't really a thread. It's the thread of execution, but it's not an actual thread itself. Now, the thread is the smallest unit of processing that can be scheduled by the OS. That's extremely important because we're going to look at some things that try to get around that. Now, what does it mean if something's scheduled by the operating system? I would suggest looking at one of the Linux kernel books. The Love book, that's the author's last name, I think it's Richard or Robert Love, has a very, very good explanation of the completely fair scheduler in Linux. It actually is a thing of great beauty when you see what these guys have done. It is absolutely amazing. It's a multi-level feedback queue, which is very sophisticated, constantly taking in information about what's going on and deciding who's going to be the next one to run. It's absolutely amazing. So what the OS is really doing, and this may be a New York reference, how many people do not know what 3-card Monty is? Anyone? Wow, okay. 3-card Monty, if you, actually Ricky J does a demonstration of it. It's a way of having 3 cards where you have, say, one face card and the other ones are the regular cards. And you're supposed to follow, let's say, the queen, and the guy shuffles them around. There's actually a trick where you hold 2 cards at once and you shoot one out. But what you're doing is it seems very obvious that it's, oh, I can see what's happening. This guy's just changing that, but it's like, and it's not obvious what's happening. It's done very, very quickly, almost too quickly for you to imagine. And that's what your operating system is doing. It's giving you the impression that it's doing more than one thing at the time, and you can follow what's going on, but it's really shuffling the cards. Now, forking a process is a very expensive operation. Between that and a context switch, it's almost a toss-up. Because when you start forking a process, I've got memory space, I have to check a whole lot of things, the kernel does all this checking of parameters, that's extremely expensive. That's why the init of the system can take so long, because it's constantly forking processes to set them up and start them running. A thread will cost you less, because you've done the part of setting up the process and say, oh, it's subservient, so I'm going to share some stuff with it, so I don't have to do that again. So a thread is sometimes called a lightweight process in some operating systems. And therefore, shifting between the threads for the context switch is not as large because there's one shared block, and it usually has pointers which point to the shared block, so you're able to do pointer arithmetic as opposed to mem copies. It does still remember a context. That's true. It does require a context switch, but the amount of memory that you actually have to copy is much smaller. If you have to copy a pointer as opposed to a whole block of memory, first of all, if you're copying memory, a pointer is smaller, and you're almost certain to find a place where the pointer is going to fit. If you have contiguous memory, you're going to have to not only copy it, you're going to have to find someplace else in memory where this aligns correctly and it can be contiguous again, and that could take several tries, and that could be going through the map. So even though these are, quote, very rapid operations, as these are happening millions of times, it gets to be very expensive. So here's a finite state machine of what happens with a process. You start out, you forked it, it's new. And it gets admitted to the ready queue saying, I've been forked, I'm ready to run.
Sorry. Yeah. Can you say again what fork means?
Fork is when you create a new process. You say to the operating system, I want a new process, fork it. Okay? So you fork it, it goes into the ready queue, and this is a gross simplification. It simply shows the states. The scheduler dispatches it, which is where the real magic happens. It goes to running, and let's say you were just adding two numbers, which is a CPU operation. Boom, you terminate and you're gone. But, oh, I want to get some stuff from the disk. Okay, well, let's see. It's not an interrupt, because I'm sitting around waiting for something, so I'm going to put you in the waiting queue, meaning that I've got stuff going on and I'm waiting for something else to occur. Oh, I've got the I/O back. I then go into the ready queue, but then I have to wait to be scheduled again. So you can see if you have a lot of data, you're going to spend a lot of time going around here. Now, Linux tasks are slightly different, because remember, we're talking about POSIX here. Linux, in absolute physical terms, has no processes and threads. It does not make a difference between processes and threads at the operating system level. Everything is a task. So when you fork, you're actually calling clone, which is a much less expensive operation because they've got, in effect, a template of what it should look like, and I'm just going to copy, mem-copy what I need, and I'm going to have pointers to the other things which will be ready, but if I don't need this part of the process, I won't set up a pointer to it until I actually need it. So let's say you had 50 things that you had to bring across, but I know that for this forking of this process at the beginning, I only need 20 of them. You're going to put 20 across and leave space for the pointers. So it's a much, much quicker operation. And switching is incredibly efficient. You can look at this later. I put it in. As you can see, it's a bit more complicated than the other one. This is the transition states for a Linux task. And one of my favorite ones is down here, because you do have zombies. Zombies are good and zombies are bad. When you send, have you ever been at the command line, you send a kill command to a process ID? What are you actually doing when you type the kill command? Sending sigterm. And sigterm is a signal on the operating system which says, terminate, please. I hope that you can exit in a graceful manner. If you can't after a certain amount of time, I'll send a sig exit, which just says, your time is up, you're dead. Now you can have zombies that will get a sig term, and they're in effect detached from the operating system, but they're still trying to do stuff. They're still alive and they're wandering around in your system. And there are some, when it gets really bad, a zombie, you can send an exit to it and it won't even die and it will just sit there and it will take up system space and resources. Usually a kill-9 will get rid of it, but that's the zombie state, which also tells you something about the developers of the technical word for it is a zombie. So you can see here reading stuff. Oh, this is something too. You won't see in all POSIX systems. This is really cool. The cursive discussion of signals. Signals are part of the POSIX operating system for which you write signal handlers. There are a whole bunch of them. They're designated in signals.h. And it says that while I'm operating, if the operating system sends me a signal, I'm going to, in effect, look at that before I look at what's going on in my program. And you can put in things to ignore the signals. If you've been using Python long enough, you know that at one point trying to use Control-C with certain things, just no way. It wasn't going to work. They've put it in so they now handle that's a signal that's sent across. One of the things you can do is you can send a signal to stop a process and look at a bunch of other signals, but it doesn't go into the waiting queue. It just stops, and then it will go directly back to active. So look at this later. The Linux scheduler, yeah, I was going to put some other stuff. We've talked enough about that. Now we'll talk about the Python-specific stuff, since you know all about operating systems and how it services all of your requests. The GIL is probably the biggest bone of contention in Python. It stands for the Global Interpreter Lock. It's a mutex. They tried using actually condition variables, but it's still a mutex that prevents multiple native threads from executing Python bytecodes simultaneously. That's a big sentence. So what does it mean? Python threads, as we'll see, are real system threads. Some things have lightweight threads, sometimes called Greenlets, which we'll see later. But if you create a thread in Python, you are creating an OS-level thread. And as we just heard, that's still something that's controlled by the operating system. It's the lowest level that the operating system can schedule. So if you have a bunch of these threads going on under your process, which is the Python interpreter, how do you keep track of them? How do you know what's going on? Well, what they do is they have a global interpreter lock. It says, while you're holding the GIL, you're holding this baton, no one else can do anything. This is the whole concept of a mutex. It's a mutual exclusion one. It's not just a read-only mutex. And look at the bibliography. If you want to know the details about this, the Herlihy book, sometimes called the Gold and Black book, is probably the best one. It has all sorts of discussions about mutexes and deadlocks and the details of it. But in fact, Python is saying, while I've got this, I'm not going to let any other Python bytecode be executed. And it must be held by the current thread before it can safely pass it off to another one. Now, that's a good and a bad thing, because if you're writing C extensions, you don't have to worry about anybody else coming in and doing stuff with your threads. I've got the baton. No one can do anything else. However, how do you know when to pass the baton? That's the problem. Depending upon whether it's 3.2.2 or if you're using 2.7, you can get what are called GIL wars. It was about, I think it was 5 milliseconds when they would look, say, have you got it? Have you got it? Have you got it? It's like having your child in the back and saying, are we there yet? Are we there yet? Are we there yet? No. No! Okay? So what could happen is I'm running, say, can I have the GIL? No. Oh, I'm through. Someone else got it. Can I have the GIL? Oh, no, somebody else took it. Can I have the GIL? And this will constantly going on, and it adds a huge overhead. So 3.2 GIL is better. They've changed it a couple of times. You have to look at the latest release to see what happens with it. It avoids GIL wars, and it's much more equitable, but it still doesn't implement priority scheduling. And priority scheduling is what the system scheduler does very well. It says, okay, you may be about, I think that's, let me think about it, 144 different levels at which a task can be scheduled for priority in the Linux operating system. So it's saying, oh, number one will obviously be more important, and it calculates in a very sophisticated way, like, how important is this in terms of tasks in general? How long has it been waiting in relation to others, etc.? But the GIL just is your little child in the back seat saying, are we there yet? Are we there yet? Are we there yet? Can I have the baton? So there's no priority. Everybody is equal. Now the GIL can cause IO-bound threads to be scheduled ahead of CPU threads, which is really weird, because that generally shouldn't happen, because things which are CPU bound almost always get scheduled first, because they tend to be quicker, because it's a mathematical calculation. They also do not block. So if you're doing video rendering, you're probably doing some blocking, but most of it is CPU bound. Or if you're using gzip, which has a lot of floating point, it'll be at the CPU. And you generally want those first, but because of the way the GIL works, sometimes your blocking I/O can go before your CPU, so you can imagine how that slows down your program. Also, signals cannot be delivered while somebody has the GIL. It just cuts off. It says, I'm going to ignore any signals that are coming in. Now, this is a very cursory overview of it. You don't need to understand more than that at the moment. This link, Dave Beasley did an extensive talk on this about 2 years ago. It is simply the best explanation I've ever seen of the GIL. It's great. You can download the slides. There's also a video of it from a Chicago Python users group that he did. So the GIL, to emulate the concurrency of execution, it regularly tries to switch the threads, right? So the lock is released around potentially, how you figure that out is interesting, blocking I/O operations like reading or writing so other threads can run. And the system overhead for this is you've got Python trying to figure out what it wants to do, and you've got the overhead of context switches and mode switches. And the really weird part is, because of the way it works, if you run it on a multi-core machine with threads, almost 99% sure it's going to be slower. By using more cores, you can actually slow it down significantly using Python threads. So this is what you need to know for today, that the threaded programs on multi-core machines can run significantly more slowly than on single-core machines. Does anybody still have a single-core machine? Do they exist anymore? Okay. So sorry?
Dave Beasley.
Yes, Dave. There's probably some VM from '78. The exception is that sometimes when there is an extreme amount of blocking, because so many things are going into the ready state, like if you're looking at multiple sockets, threads could be an easy way just to get a performance boost. But if you're using persistent storage, don't even think about it. Quickly, the Python 3 GIL. Antoine Pitrou, who has been the GIL expert for 3.2, I don't know if he's here this year, but if you find him, talk to him, a very smart guy. It introduced the notion of a check interval. Take a look at the code. You can adjust it, and you can have a greater effect than you could in 2-point by looking at the sys.set switch interval, how often you wanted to try and switch between. So why do you care about it? Because it affects system threads, it affects performance, and you need to know how it understands if you're going to write any C extensions. So that all being said, let's start with persistent storage. I have a 60 gigabyte weblog. This actually came out of something I had to do for a client. I want to find each record that has a user, SSB RTG in this case, and there are a couple of ways you can look at it. So let's go over here first. The first way maybe you want to try is brute force. Actually, Ken Thompson said brute force is highly underrated. Why? Why make it more complicated at first? What happens if you discover something that doesn't work? Don't start optimizing until you can figure out if it works. Plus, Python's buffering of files is really, really quite efficient. So this is pretty straightforward. You open the file, read a line in, say, is the target username in the line? If it is, increment records matched. Now, this operator here, what's the big O of that? What's the time complexity?
N squared.
Why n squared?
It's a string within, matching a substring within a larger string.
It could be that. This tends to be n, because it will go across and find it and just go chick, 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 chick. So you're going to deal with linear time in that, which it can be on a record that's several thousand bytes long. And what if you're matching at the end of each line? You got to go all the way over. So how did that actually work out? Well, let me go over to here. Now, I wrote it in C. I wrote it in Go. Then the Python I ran with 2.7, PyPy, and stackless. Take a look at that. These are all the same version of Python. And your difference between the fastest and the slowest, Python 3 was the worst in this case, which is not surprising because Python 3 finally made the move to UTF-8. But when they did it like Java. They said, I'm going to have 4 bytes, so they're always lined up in 4 bytes. Whereas opposed to Go, which uses, if I only need 1 byte to store this code point, I'm only going to use 1 byte. Which kind of surprised me because Go is a compiled language and I use the same blocking size as Python 3 and it was actually slower on the disk. But you can see just by choosing your version of Python on probably the worst way to approach this problem, you have a difference of almost 8% in processing real time. Now, a rule of thumb is if you can do 2 to 3%, that's good. If you can increase something by 5%, that's great. Anything greater than 5% is just fantastic. If it's more than 10%, I mean, that's monumental. Okay? So the next way to look at it said, well, instead of using the in operator, why don't we use regex? Because everybody knows regex is faster, right? Maybe not to write, but so. And in this case, I compile it first. And Python 2.72 has a C-optimized version of regex. Okay. So, whoop. That's a fluke. After I bought this, I found out, this is not a joke, this clicker is optimized for Microsoft Windows. So sometimes it will freak out with Ubuntu. So basically the same thing. We're reading it through, except this time we're saying do a pattern match instead of doing an in. So over to the next one there. Now take a look at the way the contours of the blocks go. And this one's going to be Python only. Look at that. And oops, it's off the screen for Python 3. Let's see, can we? This thing is cutting down. I had it sized for another monitor. Well, can we get it across? Yeah, it worked just in there. Okay. So there's your difference. Look at that. Now, stackless, which is usually pretty cool, just doesn't like regular expressions. So your difference is, again, between 7 and 8%. So what would be the, let's see, let me make sure I'm doing the right. So the next one would be, well, why don't we try some threads? And of course,
Why is PyPy slower?
good question, isn't it? And I don't know, because everything about PyPy has been, wow, you know, it's faster, it's got the jet. This is what happened. In each one of these tests, I'll tell you, I ran them 5 times on the PC. I took out the highest, I took out the lowest, and then I took the average of the remaining 3 times. And I did 2 sets of 5 for each one of these tests. So that if I did one set of 5 and the second one came out and I did the averaging, it was significantly different, and I had to throw it out, and that only happened in one case. So I can't tell you why the PyPy is slower. I expected it to be faster. That's something I want to talk to the PyPy people about when they're here. Let's see, big file, chunks. Oh, okay. Let's go back here. So, big file, chunks, threads. Yeah, there's one big file. Okay, there we go. So, the next thing that seems to make sense is, okay, well, I know that threads really aren't going to work, okay? Because I know for persistent storage already from what we've talked about that it's going to be slow. So why don't we try to parallelize it? What if I've got 4 processes on here, so what if we cut the file into 4 chunks, equal as much as we can get? And what the code does, let's see, you can look at it later, it's farther down, is we go through and say, try to cut it into 4 equal pieces, but if you get to the end of this piece by doing an fseek, keep going forward until you hit a new line. That way I can read everything, the chunks, as lines at a time. So there may be a couple of bytes difference, but you've basically got 4 chunks which are running at the same time, and they're blocking and they're in threads. So that this guy says, I need to get something from the operating system. Oh, I have to wait? Okay, let me switch over to the other thread over here, let him do something. So you're playing three-card Monte. Now, nothing really spectacular in here, but I will say I'll bring up the concept of queues and a very strong concept in parallelism. Even though a process and threads share memory, don't do that. That's like a dope slap in your code review. Do not share memory to communicate. You want to share memory by communicating. And the easiest way to do that here is with a queue. Python makes that very easy. You have a queue where you put things in, and it will automatically synchronize it for you, so you don't have any contention with two people writing to the queue at the same time and overwriting each other. Does anyone know the joke? Like, why did the multi-threaded chicken cross the road? To other side the get. That's funny till it happens in your program. So that's all taken care of by the queue. When you've got information, put it on a queue, and this will be your typical consumer producer, right? I'm producing how many records were matched. I'm putting it on a queue. Somebody's going to consume it, take some of that, and print it out. So think about what we've got. We've got these 4 streams going at once in threads. Somebody's blocking. I'll let you do something. So it all sounds really nice, right? Let's see what actually happens. Chunks, threads. And again, the screen. Okay. So Python 2.7, you can see that and stackless are really slow. PyPy and, there we go. Look who comes out to be the winner this time. Its data could potentially be 4 times as large because of the way it's storing UTF-8, but it's 6.4% faster. So that shows you what the overhead of the context switches and dealing with the GIL can be. Python 3 is clearly the winner in this case. Now, one of the other things that you hear about a lot is generators. How many people have used generators? Good. Okay. Now, for pure performance, what a generator will do for you is it will save you memory in general. For example, if you need a list of 1,000 numbers, and you allocate that list, it's 1,000 bytes. And if you have 1,000 processes, that's 1,000 squared that you're going to be using. So if you have a generator, you're saying, only give it to me when I need it. Give me one at a time so that your memory footprint is about that big. Now, this is the hello world of generators. Okay. Here's M. You say, count down M, print X, and you've got the word that makes it a generator, which is yield. Now, let's talk about what a generator actually is. So it's a function that returns a generator object. Okay? And the generator object executes the function itself only when the keyword next is called. And we'll walk through this in a moment in debug. And the function executes until it reaches the yield statement. Yep.
Isn't it a function that returns an iterator object?
No. It actually returns, we'll see, it's actually a generator object. Because there are other things that can return things from iter tools that aren't generators. They act like them, but a generator will actually return a generator object. And yield produces the result, and execution halts until the next invocation of next. So what you're doing is you're saving state without having to save state yourself. So let's step through. Generators. There we go. Come on. Okay. Now, let's put a debug right there. No, I don't want that. Okay. And we'll bring it down. So, I'm going to go through step by step. So now we're saying, actually, let me pull this up and answer the question for you. This is Wing IDE, by the way, of what I'm using. Okay. So we'll say debug probe X. And there's X that's been returned from countdown, and you can see what it shows up as. At the bottom down there, it's a generator object. Okay? So if I go step by step, oh, great. Generator has no object. Oh, because, let me do, okay. I tried to make this compatible with 2 and 3. This is a good point to bring it up. I wrote this in 2 and then shifted over to 3. Simply syntactical. In 2, you can say generator object dot next, but you have to wrap it in next if you're in 3. So now let me just go back. Say there. There we go. So now I've gone into there. What happens next? So what is n equal to right now? N is equal to 10. So I hit that. And what do you think it's going to print out? Well, what are we printing out? It's not printing out n, it's printing out what the generator has returned. So nothing when it went through there, because 10, watch. So watch where the number actually gets printed out. So you're saying here, yield, then it prints it. And when it goes back, so we'll start from the beginning again. There. So you've yield. That's where it's holding, saying, listen, I've stopped. I've yielded the end. I'm going to save the state until I come back in. Then I'll decrement it and go back around. So yield is a point in your logic where saying, give me a result and then stop processing, save the state. And when you come back in, I'm going to come back to that same point and continue again. So in this case, it's a very simple example of getting consecutive numbers with a maximum range of 3 here. But if I bump this up to 1 million, and I'm running it in parallel, what does this take? This takes just enough memory to put this on the stack and one execution of a CPU command each time. If I had had the 1 million in advance, I would have been, think about that. If you had 1 million and you had 1,000 processes going. It also makes it very quick, because once it's on the stack, all it is a CPU instruction that's passed right back. Now, why is this helpful for, whoa, that was interesting. Okay. If you don't know everything is in itertools in the library, I strongly suggest taking a look. It is one of the coolest libraries in all of Python. You even have, in the latest releases, some combinatorics. You can have generators that do permutations, like n-choose, well, you can do combinations and permutations. You can have n-choose k and npk that are set up as generators. Stick in 100 and see what happens if you actually had to do that in code yourself. And you could then do that and have a memory footprint that's big. Okay. This is one of the other really cool things that people don't use this enough, called chain. You're saying, I have a bunch of strings that I want to chain together. Okay. But I don't want them stored as one big string all at one time. So look how much code is required for that. Now, the disadvantage to this is once you have taken something from a generator, you can't use it again because it's giving it to you one at a time. It's not like a list where you can go back. So this is a decision you have to make. But if you know that you're only going to iterate through something, this is a huge savings both in time and in the memory footprint that you're going to use. And what generators can do for you is they can give you pipelines. Now, you know how in Unix you have the pipe symbol? You might say, grep, look for something pipe wc-l so that you can count the number of occurrences inside the file. You can do the same thing with pipelines. Now, you can create a function that receives a value and emits a value. Starting to sound like a coroutine, not quite. And you can hook these together, and it also makes very good code, because you know that if you've put together something on the Unix command line, you have orthogonal units. What is orthogonal? I realize I use that. Somebody tell me what orthogonal means.
Angle of 90 degrees.
In a computing sense. If something is orthogonal, it's...
Unaffected by? Independent?
Yes, independent. Each process does one little thing, what Unix was originally intended to do. And then you take all these things and you put them together, and you have a pipeline, and you see a sequential process that it goes through. And, oh, I want to take that out. Guess what? I take that out, and the pipeline isn't broken. Or I need to put something in at this point. You're not touching anything else. The individual procedures which are required don't need to be changed. So you don't have this one with a lot of if statements and branching off. So let's take a look at the code first for, was it big file pipeline? Big file pipeline 1, that's what we want to look at. Okay? And I've got some extra code in here because this is actually something that I used in production on a client site that had gazillions of huge weblogs that had to be gone through to get information on a constant basis. Now, this one I put in if there's zipped files, we'll automatically unzip it for you, etc. But the interesting part is down here. Okay. Let's go up to the starter. Okay, let's do it for y. Oops. Sorry about Y, I, E. Okay, so your starter is your opener. You give it a file name, or in this case, you could put in a list of file names if you wanted to go through a bunch of them. And then that yields what? What's that? It's going to yield the result of this expression. And before we go forward, just make sure we clear. What is the difference between a statement and an expression? Somebody tell me. You. Yeah, a statement is a statement. It's a declaration. An expression is going to be evaluated every time that the code is executed, or every time that it's seen in the code. So this yields it. And let's go down for... Okay, so here's our starter. So we send it the file names. It's going to send back. Now I said files because if I had passed it a list of file names, it would give it back to me one at a time in a pipeline. So I've now got a file from a generator, and the cat is also a generator which says, as I yield a line one at a time, I will only send the line back, and then I send it to grep, which gets a line and a pattern at the beginning, and it will yield a line. Now that sounds all well and good. So let's just walk through and see how it actually gets executed. Go to here and say 5. No, I don't. Shoop. There we go. Okay, so what is, look what's happening here. Okay. So what happens, it went through and those generators all got started. It looked like you were calling them for execution, but what it did is says, okay, start a generator, but you haven't asked me to do anything yet. The first time you call a generator, it's just creating a generator object, but you haven't started to generate yet. Be careful about that, because if you don't understand that you have to prime it first, it's going to look like you made a mistake. So now I have passed it lines. Whoa, what happened to that? Okay, so open the name. And this is the part that can be confusing, because you've set up the generators to talk to each other in a pipeline underneath, but if you step through it, you're only going to see how they talk to each other, so the code doesn't actually execute the way that it looks like it's going to. Okay. Take that and play with it yourself, because you can see what's going on, but it takes a while for your mind to put it in. But what does that do for you in terms of performance, if anything? Well, we'll go to pipeline. And with my Lambda screen. That surprised me. Look at that. Again, Python 3, which has the larger data, is the clear winner, this time by 11.5, so we'll round it up to 12%. So we've gone from using a big file brute, which wasn't that much different, to if we just use simple generators and we pick the right version of Python, within that best pipeline algorithm, we have a 12% increase. Okay. Now, but is that the best we can do?
Sorry, the 12% increase was compared to the brute force?
No, compared to the within pipeline algorithm itself, the best and the worst performers. We'll show a comparison of worst and best at the very end. So, yield then became an expression in Python 2.5. This is why I talked about the difference between an expression and a statement. So here's an example. Now the R value is an expression. You put parentheses around it, but what does that do for you? Well, that gives you the concept of coroutines. Now, coroutines is this word like concurrency and parallelism. It's thrown around all the time. So actually, if you want to see a great talk, look at Peter Portante's talk last year when he talked about it, because it kept bugging him what it was, and he did some research on it. So coroutines in Python use yield as an expression, which allows you to create coroutines. Well, that doesn't tell me much. Coroutines will execute when values are sent to them. Generators, we just said next, give me back a value. We're now saying, I'm creating something that can consume a value and give me something back. That's what the yield does here. It tells you why it's different from a generator. A generator only produces values, and a generator is used for iteration and to create very efficient iteration. Coroutine can both consume and return. So, what is a coroutine in computer science? Well, the first reference of it is in one of the Canute books from 1958. He was having a conversation at a table with M.E. Conway. If you don't know him, he's a really cool dude. He's still got a website up that looks a little bit like Peter Norvig's, like they don't care about HTML, but the information is there. So they were sketching out something. They said, well, what if you could consume and put out values? And they literally wrote it down on a piece of paper. And it wasn't until 1964 that Conway wrote a paper about this and said, coroutines are functions that save control state between calls. In 1964, this was monumental. And that kind of disappeared. What happened? Okay. Somewhere in this, around 67, is actually a program in here, you can look at it. It takes the concept of the dining philosophers, and it emulates it. Who has not heard of the dining philosophers? Ah, okay. This comes out of Dijkstra trying to deal with several tape drives. And which one do I read from? Which one can be backed up at this point? And originally it was spaghetti with forks, but it's now primarily done with philosophers and chopsticks. That being said, you have a bunch of philosophers sitting around a table, and there's a bowl of rice in the middle. And philosophers aren't very smart. They can either think, or they can eat, or they can sit there and wait. They can't do more than one thing at a time. And in order to eat the rice, you need 2 chopsticks. Every philosopher is given 1 chopstick, and then the waiter gives 1 other chopstick. So only the person who has the 2 chopsticks can eat at any one point. So Bertrand Russell starts to eat, and he puts it down, and he passes it to Confucius, and Confucius can now eat. Now, how does he decide to pass it to Confucius? Good question. That's where the whole concept of scheduling comes in. What if Confucius is his friend, and they just keep passing it back and forth? The other philosophers starve. And that's literally the word we talk about, is thread or process starvation, if you're not getting your time in there. So this was, okay, wow, I can give you the chopstick, so you have, which is like a mutex, or what do they call it? There's another name for it. A monitor lock. That's when you get conditional objects. So what if I could have something where I not only just give you the chopstick so you can know how to run, but I give you a note with the chopstick and you give me a note back, and we can eat and we can do philosophy at the same time. It's like, wow, this is really cool. So it kind of died out. It just disappeared. But we'll stick with the Python stuff for the moment. Now, you have to prime a coroutine. It sits there, and There's a decorator that Dave Beasley came up with, which is just like so simple, but makes your life so easy. I saw it was one of these like, oh God, I can't believe I didn't think about that. And it is in there. It is. Let's take a look at Coroutines 1. And if you thought generators were difficult to follow. Okay. Now, all the coroutine does is when you create a coroutine, nothing's going to happen until you've primed it saying, okay, I'm sitting there, and you go, you send it some, say, click, okay, I'm alive. That's what the decorator does. It automatically takes it and it primes it for you. You can take a look at the code later. It's very simple. So, let's see what happens. Thank you very much. No, I don't want to do that. Okay, so now we're on. Here's the decorator. So we're saying, while true, yield S. But what is S? Is there any argument that we've sent to this? So this is what we're going to do, is we're actually going to send it something. Because it's sitting there, I want to say a little bit like a socket, but not really, waiting there to consume or to be sent a value. Remember, it's not a value that's a formal argument. So I send that over. Bang. Actually, let me bring up the standard I/O. So we'll say bang. Okay, so it's now sitting at the yield, holding the state of what was there, waiting for another value to be sent to it. I sent, I'm leaving now. It prints it, goes back to the yield, freezes, and then the program finishes. So you can see that it will always go zoom, and it's back to here, waiting, literally, right here, until another value is sent to it, and then it causes the assignment to occur. So, let's see, is that, now, would this do anything for processing a big file? What do you think? Can you see any way? I mean, just think about it. We've already got generators and pipelines, and it's like, well, is it really going to do anything for me? It's certainly more complex idea to deal with. So let's see what that would look like. Also, too, when you download this, I'm giving you the 60 gigabyte file in compressed format, so when you go to GitHub, don't be surprised how big it is. Okay. Now, let's look at this code. Now, we have the pipeline like before, and I called it opener instead of starter this time. And you can see we set the opener and we send it, but look at the way that the individual processes are constructed now. They're all coroutines because, well, how do we know they're coroutines? Because they have yield as an expression. That's what tells you it's a coroutine, and I put the decorator around them so each one of them is primed. So, some of these have arguments. The other ones didn't have arguments, but it's called target coroutine, because a coroutine can consume and it can send. So I'm saying, here's a value I'm sending to you, and here is the name of the procedure to which you should send this. Okay? And notice it's a variable. So if you have a more complex event loop on top, you could send it any coroutine. It's not coupled, it's orthogonal. And it will send it to wherever it wants. So think about this, that you have these things that are defined, say, I'll receive something, I'll do something with it, and then I will send it off to wherever you have told me to send it. And I can do that on a dynamic basis. Okay. So, is that going to help at all? Whoops, go over to the spreadsheet. And we'll go, I'm calling this pipeline 2 because it's pipeline with coroutines. And, again, adjust for the screen. This is even bigger than it was on the other pipeline. It's only a difference of 3.41% because coroutines are so efficient. But again, Python 3 is very clearly the winner in this. And we'll see how this compares to the other ones at the end. So I will tell you, since you haven't been keeping track of the figures, that in terms of real time, this is the most efficient thing that we've come across since, or so far. Because you're limiting your memory, because it's a generator-like object, it's that big, and you're not setting up stuff on the, think about that. When you set up something on the stack and it's static, it can only send to X number of places. And if you want to go to X number of places, maybe you have a big if-then-else statement. But if all it has to do is, in effect, it's taking an address of where this other coroutine is sitting, that's point to arithmetic. So bang, 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 bang. You've cut down your processing time enormously. So, yep, go ahead.
Have you tried to process this 60-gigabyte file with just grep and WC?
Yes.
And how does that compare to Python's?
It's a little bit faster most of the time because you don't have the Python interpreter and you're running a C-optimized program. But the difference, I forget what the percentage was, but it's like that big. And again, this is just one example. I mean, if you do with anything which is C-optimized, generally it's going to be faster. But in your Python world, now, I did this with a file. What if you have a database? What if you have a database from which you need to get lots of different information? Where is your bottleneck likely to occur in that process, giving all of the things being equal?
network sockets?
Not necessarily. Something a little bit bigger, higher level of abstraction. The database driver itself. Okay? Database drivers, and the reason I didn't use it is because database drivers vary enormously. Does anybody use MongoDB? Wow, that's more than I thought. Okay, PyMongo is probably the most frequent one that's used for it. That's maintained by one of the guys at Bitly. And I talked to, just before I left, one of the programmers at Tengen that makes Mongo. And they've been investigating that, and he's going to be using something we'll talk about later to make it even faster, because there's a ton of blocking which goes on in PyMongo, so that you can be as fast as you want with the other stuff, and you're going to have badly programmed blocking that's going on in your database driver, and it's just going to kill you. This is why I picked a file to do it, because you took that out, and in effect, my operating system is my database driver saying, get me the stuff. Now, apart from it being faster, because we're just talking real time, it gives you an enormous amount of flexibility. Think about this. You had an event loop that can send data to a collection of coroutines that send out diverse tasks, and depending upon what you decide in the event loop, they can all send it to different places at the same time. Now, that's going to be something that we'll see in about 5 minutes, because that's the basis of a lot of the frameworks that purport to give you better performance. Python generators would be great if we had non-blocking I/O, because for this case, remember, we're blocking. I'm going to the operating system and saying, give me a chunk of data, whatever I'm using for a blocking size, and it might be able to give it to me all at once. I might have to wait. I have to wait for the operating system to give that back to me. If we had non-blocking I/O, and we'll talk about that in about 5 minutes also, it would be a lot faster. But the logic behind it is incredibly difficult. In fact, we talked about that in the open space, and that was one of the things Guido brought up. Should we make everything non-blocking I/O? And everybody said yes, and they said, who wants to do it? And the room was silent. It's really hard. So, we'll do a little interlude on worthwhile optimizations, because everything is compounded at scale. If you have 5 processes going, well, this is a good question from what you know so far. If you have 5 processes going and they have the cost, what is your real-time and system cost going to be? It's probably not going to be 5 times because you've got it running in parallel. Or is it just going to be the same cost as running one? Well, what are your costs that you have to look at? What are the context switches that are occurring? How much blocking is going on? These are things you need to think about, that if you start putting things in a parallel, it doesn't necessarily mean that what you save here won't be offset by something on the system side. So remember that everything is compounded at scale. If I'm doing one thread, I don't have any context switches. But if I have 30 threads, and they have to do context switches between themselves and do blocking I/O, that can get kind of expensive. Everything is compounded at scale. If you think it's going to be a problem when it's single-threaded, it will be more of a problem as you go to scale. And this is something to get used to. Everything breaks at scale at one point. No matter how intelligent you are, no matter how good your system is, your system will break at scale. That's why probably the hardest job to get at Google is a site reliability engineer, because they have to know infrastructure, computer science, programming in at least 3 languages, how the OS system works, and if somebody who's a programmer comes up with a new thing for App Engine, they have to know how it's going to affect the performance of the entire infrastructure. So just be ready that everything's going to fail. There's a little directory on here with some optimal things that you can do. A couple of them are list comprehensions over loops. If you have very small values, you're not going to see the difference. You run a test with large values, they'll be significantly faster. List comprehensions are significantly faster. C decimal versus decimal. If you're using the Python decimal library, excuse me, does everybody know the decimal library, or perhaps you don't have to work with it? So when you want to take floating point and make them look like real decimal numbers that you work with on paper, it's very nice, but it's kind of slow. There's this one called C decimal. It's literally 10 times faster for large values. Once you get up to large values, and it works exactly the same way, so all you have to do is change your import statement from decimal to C decimal, and it's 10 times faster in all your decimal calculations. Then multiply that over scale, you'll see what happens. Memoize redundant calculations. What is memoization? Somebody explain that to me. Well, caching is the overall. What specifically is memoization?
If a function has seen the same parameters before, then return the output that it generated before.
That's it.
Don't recalculate.
Well, yes, it has to be, yes. All of this, almost everything has, if you're going to use memoization or you're going to be doing parallel things, we're talking about deterministic processes, because then you get into the concurrent aspect of it. But memoize is, yes. If you have squared. Well, let me see if I've got the, I did it for, has Fibonacci as their favorite sequence to do stuff? Oh, yeah, okay. One weird guy in the back. Let's see if I have that up here. Okay. I just did it because mathematically it's something that's very easy to use. Now, I ran it for 20, 30, 40, and 43, because 43 is this magic number in the Fibonacci series where things start to take longer and longer with each time that you increment. I just didn't have the time to do it. It's also when you get to 92 or 93 is another one. It's also where Java will die, because it just runs out and you get memory errors. I actually took one PC and let it run for several days and calculated Fibonacci 1000, which was very interesting to do, but only do it once. And Go ended up being the fastest because Go will never blow its stack, and you can use a recursive one, and it will just keep going into swap space. But for this one, here's Fibonacci in Python, but with a memoized version and a non-memoized version, if I can get it across. So for 1 and 2, which are the 10 and 20 Fibonacci, no big difference, right? And you know that in the Fibonacci sequence, there's a lot of repeated calculations, which is why I used it. So instead of repeating that calculation, which in and of itself is pretty simple because it's basically addition, I memoized it. So orange is the memoized version, and blue is the non-memoized version. Okay? Literally, it's flat. You just keep getting larger and larger, and the memory access is so quick that it's just amazing. So think about this at scale if you're going up. And it doesn't have to be obviously Fibonacci, but if you have something with redundant calculations, and you memoize it, and you have 1,000 processes going at once, you have almost linear time. And there's nothing really complicated in the algorithm. You can take a look at the optimal subdirectory, and it will show you how to do that. And this was on memoizing versus caching, which this gentleman just explained. Now, I/O. How does it work? Everybody knows what I/O is. Oh, there's buffered I/O, there's unbuffered I/O, there's blocking I/O, there's non-blocking I/O. But what is really going on when we do this? Okay? So here's buffered I/O. You get some input coming out of the hardware. It goes to a buffer in the kernel. Now the kernel, for each one of its processes, keeps a stack in the kernel for each one of the processes and buffers for that individual process. So it sends some stuff to the buffer, and this usually, because you're trying to read, which is file descriptor and the length. You're saying, here's the file descriptor, I want to read n bytes. And then it comes over to a buffer that you have on your side, and Python knows how to read from that. If you go on the other side, it just works in the opposite direction. But you can see that it's buffer, boom, bam, bang. Now, if I'm asking to get, I don't know, 10,000 bytes, does that mean I'm going to get them all at once? Because I don't know how I'm going to get them from the disk. I don't know when the kernel is going to get it. So I got to wait till this buffer's full before I can actually read it over, because that's what's going to make it efficient. The kernel says, I'm doing my job, you wait till this is full, then you can have the stuff, and then you put it into your buffer, and then the program can read from it. So what that can do, as we saw in our diagram, if something's blocking and waiting, it can cause it to, in effect, go to sleep or go into the waiting queue again. And this means that, remember that word, the thread of execution and the I/O run sequentially. So no matter how many cores you have, your I/O is still happening sequentially at the kernel level. Oh, that was what I actually just explained. So here's how the timeline works. I make a read request. I have to do a mode switch, so there's the operating system doing something, down into kernel mode. And just because I've asked to do something, the kernel is not going to say, whoa, I'm sure you're doing everything right and I really trust you. So it has a process where it does a parameter check to make sure you're not passing something stupid. And then you've got a period while it's doing this parameter check, and there's no data there because it hasn't been able to request it yet, so you're sitting there blocked. Again, this is happening in a very quick time generally. Oh, okay, I'm waiting. Oh, the data finally arrives. Then I have to put it through my buffer. Then I have to do another mode switch to go back again, and it goes into my user buffer. I read it, and it's finally fulfilled. I tried to make this about as proportional as possible. So when you do a read and you just see something coming back, you've got all this stuff going on. Now, since everything happens sequentially, if you have a bunch of people doing this, they're all asking for this to be done at the same time. And while we're doing this, this is CPU, so no one else can do anything. So maybe here, if I'm blocked, I might have to do a mode switch and come back, start this thing over again. Okay? Because the kernel, in effect, doesn't want to wait for anybody. It's very impatient. Say, listen, you haven't got your stuff? Get out of here. I got work to do because I can only do one thing at a time. All I can think of is this, like a Terry Gilliam cartoon where this guy has stuff coming. No, boom, boom, boom. And that's exactly what the kernel is doing. And again, I'll drive home the point. It's sequential. So here's an example of blocking I/O. Okay? And I wrote it in, it's probably the lower level, as you can see, using an OS, right? These are the lower level system calls which are available to you in Python so that we're actually emulating the process. Because, again, Python abstracts a lot of stuff out, does buffering, does blocking, et cetera, for you. So this is what you're going to do. Say, if text is lower, okay. Actually, I bet we can probably run this. And that would probably be the best demonstration. See. Make sure this is the directory for it. Yeah. And we'll do it just with 2. Okay. So I'm sitting there blocking, right? I'll type my name. Okay, that's easy, right? And now I'm sitting there not doing anything, but it looks fine, right? The prompt's just fine. Whoops. So that, in effect, is what doing when you're getting command line inputs. You can take a look at this later to see exactly what it's doing, but it's being very obedient. It's being very nice. It's blocking. And meanwhile, while I'm sitting there waiting, the kernel is going off and doing other things, but the user experience is good. Now, there's non-blocking I/O. And that's an I/O operation that doesn't cause a thread of execution requesting the I/O to be blocked. Oh, that should be blocked. Just write down file 56, blocked. It doesn't cause it to block. the thread of execution, the I/O operation, still runs sequentially. So what's going to happen? The thread of execution will be notified when an I/O operation is not initiated or partially initiated. And you must tell the file descriptor itself that is non-blocking before you start. Oh, damn it. Okay, so here's how non-blocking works. Read-write returns an E-would block. That's a system constant. Okay? If it cannot complete an I/O operation, which means I've requested 10,000 bytes, I can't complete it, I get an E-would block, and read-write returns the number of bytes in the I/O operation. Now at that point, if you're writing at a lower level, you can say, okay, do I want to wait for the buffer to fill up? I got 3 of them there. Is it worth my while to take it across? Because remember, you're not blocking. The operating system has given it to you. It's going to go on its way and not tell you about it again. So this is how this works on a non-blocking timeline. You request your read, does the parameter checks. There's no data. Oh, the data arrives, boom. And the data may not be everything you requested or a full buffer. You're going to keep going back and forth. Now, you can see that there are mode changes here. This is where you're going to have to balance the cost of blocking to a mode switch. And it's going to become clearer which one is more costly. So remember this, that non-blocking I/O waits for no man. If you say non-blocking, that's exactly what it is. You better take care of it and go on your way, or you've lost your chance to do it. And what if there is no data for some time? What would happen? So let's do the non-blocking. Oh, now I can type quit because it's been sitting there blocking the entire time. Okay, non-blocking. Oh, there's more than, yeah, I think it's 1. Yep. Non-blocking 1. Okay, so I'll type in Bob. You said Bob. Now, if I sit around in a while and we'll talk about something else, what happened there? Because I'll show you what the code does. I didn't have any of the nice blocking, which is part of our standard Python. And you're probably thinking to yourself, why would I want to do this? Okay, so where's the file? Okay, so this is a cheesy thing I did to have it not die right away. I put in a sleep, which, believe me, I've seen people do stuff like this in code. You don't want to do that. This is for demonstration purposes only. If I had not had the sleep there, what would have happened? It would have gone, boom, right on its way. Okay? The operating system wouldn't have been waiting, which could be a good or a bad thing. Let's see. So, we create a procedure that we loop over that handles the exception that occurs when you haven't put in the I/O. We can say, Control and we'll go to non-blocking I/O 2. And if you want to see really ugly code, you can save this and show it to people in code reviews. Because this is like, it will work, but it's ugly, it's complicated. Well, read val is none. Oh, I'm getting an OS error. Well, if it is E-would block, then I want to raise it, but if the read val is none, oh, and then I have to go down to the file control level to get all this stuff. So, will it work? Yeah. Is it efficient? No. So why are we even looking at this? To see that there are better ways. And what about select? Select isn't used that often. Select returns a bit mask of all the available file descriptors, which means what? I've got, now file descriptors, remember, in POSIX are not just files. They could be sockets. They could be any stream. So give me a list, in this case it's a bit mask, so it's very efficient, of all the available file descriptors, and mark the file descriptors that are eligible for I/O. That either means read or write, because you have a bunch of them that aren't doing anything. So it is O of n because it's looking at it in a linear way like that. Again, it's a bit mask, so it's a lot faster, and it uses up to 3 bits per file descriptor. How many file descriptors would be open on, say, an average laptop if you're doing something? 5, 10, 1,000? Thousands. So What we just did with the non-blocking I/O, if you use select, every time that you call select, it's going to return, say, 5,000 of them, which is 5,000 bits times 3, that's 15,000 bits, and then I have to go through, so that's O of 15,000, because I have to read each bit. So that gets to be a little expensive. Now there's also poll. Poll is not available directly, I believe, in Python, so you have to get down to the C level. And this is what's been used in systems programming and is used underneath for writing things like Python. It returns only the registered file descriptors, saying these are the only ones that I want to pay attention to for I/O, for my application, for example. But it uses 64 bits for each one of them. So if you have 2,000 files, that's 2,000 times 64 bits, and again, tick, 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 tick. It's linear O of n. It will only signal the presence of an unserviced file descriptor if it has I/O that's pending. And the I/Os will continue to be reported until you service them. So let's say that you get 3 files back that have I/O pending, and you only do something with 2 of them. You call it again. They say, don't worry about it. I know you haven't done anything with it yet. ePoll, this is my favorite. I love it. Edge poll. This puts the onus on the programmer like you wouldn't believe, but gives you an enormous boost in performance. It signals a change in level on the interrupt level. If there is a file descriptor to be serviced, you are notified only once when it occurs. If you don't catch it that time, you are out of luck and you have lost it. But it's very efficient and it's very fast because it only tells you what's there, gives you the one chance on the, it's like living on the edge. You haven't got it, you have fallen off. And it's by far the fastest of all the calls. So dealing with things at that level gets to be really complicated. So people decide, we need to have some level of abstraction. And around 2001, libevent came out. And that was a wrapper that provided a mechanism to execute a callback and made all this much, much easier. And then around, I think I have the actual date later for libev, which was harder to deal with. And also by 2007, so many of the C programs had libevent as a standard part of it. This is why I asked the question, why aren't people using Python 3 more? Oh, because the libraries, and I'd have to restructure all my code. Take that, and this is what the guys were dealing with in C. But libev is loosely modeled in libevent, but it got rid of all the bugs, all the limitations, and it is much, much faster. Which now brings us to the concept of Greenlets. But Greenlet comes from stackless. If you don't know stackless, Python stackless, take a look at it. It's really cool. It allows switching between the coroutines like we have seen, but it allows on a lower level on the actual system stack that you can switch between coroutines at anywhere on the stack. Think about that. Anywhere on the, if I've got something down here, a bunch of, oh, I want to talk to this guy, I know how to switch to here for context automatically. We'll show you how it does that. It's written in C and assembler, and it actually manipulates the process stack. It takes pieces of the stack, saves them, puts them on the heap, and as it becomes necessary to put it back in, it will take something from the heap and put it back on the stack, which just hearing that scares me, but it works. I mean, think about what's involved in that. That's really impressive. And I don't mean to push that aside, but there are security implications in almost anything once you get down to this level. And that you can balance off like, okay, how much is a security? Because it's going to be only within the realm of stackless. It's also, it's pretty well protected. And it's only on the process stack that stackless has access to. It's not going to be going out to other, like it's not going to be going to the kernel stack and saying, hey, let me take this frame out and put something else in. So it can only run in the context of a Python thread, which remember is a full system thread. So let's take a look at what a Greenlet would look like. This is going to be really interesting. Let's go. No, I don't. I love WingID, but God, that drives me nuts. Yeah, I'll say that. Fine. Okay. And we'll bring up our standard. Okay, so here's our standard. Okay. So we have nothing so far. Now if we step, okay, so I've printed, switching to 1. Now watch. I switch to 1, which is my first Greenlet. Okay? That prints. Now 1 is not going to even finish, because the next one says, you know, go directly to here on the stack. So, to a switch to 1. Now I switch back to 1, say 1 is done, and main is done. There's something a little bit odd here that you won't see when you have regular procedures. Where does it say 2 is done? Never pops up. Yeah, so is that a question you just...
I mean, wouldn't you make 2 coroutines and use coroutine.syn and get the exact same effect?
Hold on. Again, this is done for demonstration purposes to show how they work. So, this is to point out, once you've done the switch, you don't have to execute everything that you've put under a def. If you switched out of here, you never come back to it. If it were a regular procedure and you called another procedure here, it would eventually have to unwind from the stack and get back to here. This isn't. This is like a go-to statement. Okay? So while you ponder that and that scares you a little bit, so Python coroutines and greenlets. So now you can use a subroutine within a greenlet to call the greenlets, as we just did, because they're not stack-based. Remember, there's no unwinding of the stack. So if you say go to, it's going to go there, and whatever else you've got in your code may never be executed. And it allows arbitrary invocations, and we'll look at a little bit more. Okay. Let's get rid of this guy. We'll go down here. So we're just declaring greenlet 1 and 2, and we'll go here. Yes, thank you very much. Okay. So now we've got 2 greenlets, 1 and 2, and we're going to say we're switching to 1. What's this? 1 is just sub. What is sub? Well, sub is over here. But because sub is an actual procedure, it has to unwind from the stack and go back. Don't think about it too much. Look at the code later. It's to show you how you can mix regular procedures with greenlets, so you could have something that you want to require to come back and execute everything, call out to different greenlets, which call each other, and then it will unwind on the stack. Even though it's playing with the stack, since it's not a greenlet, it will unwind back to that, which says, that's like a controlling event loop. Everything has to come back to, even if we go out. And keep that in the back of your mind, because that will recur. So let's go over coroutines and threads. Now, chunks of the thread execution stack are moved on to the heap for the greenlet coroutines. And when an event occurs for a frame which is on the heap, it takes care of moving it back for you. It knows what to do. And I haven't come to a place where there's been an error. It does it extremely well. And the scheduler, is because we're dealing with threads, controls the movement of the frames. Now we'll talk about how that gets scheduled. Well, it's non-blocking I/O, so it keeps the scheduler from stalling. And they're all tied to a thread, so the operating system still has some control over the thread. But here's one limitation. You can't call a greenlet that's in one thread here and another thread here. They all have to be within the same thread. Because think about that. If we're manipulating the stack for a thread, if we try calling across to another one, that means that we'd be manipulating the stacks of all the threads and keeping, bookkeeping of what's going where. I mean, that gets to be really much more complicated, though the people at Go are trying to do that right now, trying to be able to migrate individual lightweight routines across individual threads. Now, the big point is the OS knows nothing about this, because the lowest level the OS can schedule is what? A thread. And you're doing this within a thread, so it's playing 3-card Monte with all its processes and threads, and you're saying, look over there while you're pulling cards out of your sleeve. Okay? So that's just very simple. You have a frame on the heap. It needs to be moved over. The scheduler, I use that word loosely. So here's, you can look at this later. It just shows you how the coroutine is saved. It goes back, assumes you know how the heap grows. Now, when I said scheduler, Node.js, Greenlets, Gevent, Erlang to a certain extent. All these use the same scheduler, which basically is first in, first out. Whatever gets up there, because there is no priority scheduling, because you're trying to get away from the operating system doing that. Which isn't necessarily a bad thing, because you're getting rid of all these system costs, and it's happening very quickly with very small imprints of memory. But can somebody think of the one scenario that will toast you? What if you have a CPU-bound Greenlet? Remember, that doesn't give up. So you have one CPU-bound Greenlet or coroutine there, you're going to toast the rest of your stack, and it's going to sit there. And we'll talk about how you deal with that. So let's talk for a second about the threading models that this runs under. One-to-one, most common threading model we see. Python, you get a thread, you get one thread from the kernel to one Python. Java, Scala, all the JVMs do the same thing. A many-to-one, where you have lightweight processes in one OS thread, which is what we just looked at, which is not typical Python. And then, if you're really academic, there are some people that have done many-to-many, but no one's ever been able to put it into a form that's been useful in everyday life. So the scheduling is what we just talked about, where you're multiplexing coroutines in one thread. And the reason you do that is you want to avoid the context switch, because we talked about how expensive that was. That's probably the single largest limiting factor when you scale is context switches. The schedulers are the weak link, because you can get toasted with a CPU-bound process. Involuntary context switches, well, that's interesting, we haven't talked about that. There's a voluntary context switch, which says, I'm going to block, okay, so I'm going to move myself out, go into the waiting queue. And then there are involuntary context switches, which happen, aren't always bad, but they can point to a bottleneck. That says, okay, your time on the scheduler is up, so I'm going to move you out even though you aren't finished and give you another priority. Except that generally doesn't happen with CPU-bound threads, because they're in the middle of something like a mathematical calculation or video rendering where you got a bunch of UDP packets that have to be put together. So it's not going to even get an involuntary one. But if you start getting a lot of involuntary context switches, it means that you're putting pressure on the kernel, and it can't take the time it thinks that is allotted to finish what it does. And if you start doing that at scale, and you start getting things context switching in and out, you've toasted yourself. So this is the brief quiz, just to make sure that we know where we are. Somebody tell me, what is a process? Somebody raise your hand, say it. Go.
A running program?
Mm-hmm. It's an instance of a running program. What's a thread? I have to go.
Like a process, but it shares memory with others.
Oh, yes, it's like, but what's the important part? It's subordinate. Okay. What is a context switch as opposed to a mode switch? Speak up.
Switching between two threads of execution?
No, that would be a mode switch. If you go from kernel to user mode, what would be the context switch?
Stack and program counter switch?
That's part of it. That's two out of the three things it does. But in a larger level, what does it do? You're saying, I'm moving from this process or this thread to another one. You were describing when a process or thread moves from user to kernel. And yes, there's a small cost for that. But what you're saying for a context switch is, this guy's time has run out. He's blocking. So remember we talked about, you got to do the memory copy of the three elements of it. You've got to find the contiguous memory. You've got to store the state. You've got to store the virtual memory callback address. Yes, yeah, it's the guy moving out of your cube. Somebody moving in, then you moving back in. Yeah, well, it can be. Or you can get something that says to the scheduler, hey, listen, I'm blocking for I/O. You better move me out of here. Or it could be, you have this amount of time to complete your task. I'm booting you out, which would be an involuntary context switch. It is all handled by the scheduler, the kernel scheduler. This is not something that you will handle yourself. That's all OS. So what is blocking I/O? We just kind of talked about that. Raise your hand and don't mumble. Blocking I/O. Okay.
Doesn't return until it has the value you need?
Yes, but what happens when it blocks? What happens on the operating system level?
Your process gets moved to the waiting.
I'm sorry, you got to speak up.
Sorry, your process gets moved to the waiting queue.
That's it. You get moved out, because remember, it's sequential execution. I'm blocking. Think of blocking equal to being waiting. Okay? Blocking sounds like somebody stopping you from doing something. where you're actually waiting for an event to occur. What is non-blocking I/O? Not always the same hands, but go ahead.
Essentially, you get as much data as you can right away,
And it's up to you to handle it. It's like, you've got it, you go ahead, I'm not going to block, fill up buffers. I got a little bit in the buffer, here it is, take it and go. And if it's edge triggered, you only get told that once. Now, what is a generator? I just want to.
It's a function, or it's a callable that returns a generator object, which is an object that follows the iterator protocol.
Which means it follows the iterator protocol, meaning what?
It has an under iter, and it has a next method.
It has a next method. So you're going to get what's next, next, next. But you only get one at a time. And remember, it's very little amount in memory. And the next step is, what is a coroutine? Somebody from this side. Guys over here is like, ah. Go.
Yield with expression, or yield is an expression, so it can consume.
That's true, but doesn't tell me what it does, really. How's it different from a generator?
The generator which has values as input.
Yes. Is it iterating? 'Cause that's what a generator does.
It waits for input.
It consumes and it emits. You send it a value, it consumes it, and when the yield expression is evaluated, it's in there. You may do some other processing, and then it can emit a value. And when it emits a value, does that value have to be like a callback? It can be another coroutine, right? That can be the target coroutine. So it consumes and emits, which is very different from setting stuff up on a stack. So now that that's clear, putting it together. So we have non-blocking I/O, which is much faster, but it puts a greater onus on you to manage it. Python coroutines, you avoid the overhead of classes. There should be an article somewhere, don't use a class unless you have to. I mean, not everything is a class unless you're in Java, which requires it. There is significant overhead with a class. It's a great abstraction, but if you don't need it, don't make a class out of it. We've seen that pipelines work really, really well. And Greenlets have thread-like performance, but without the context switch. Okay? Now, these are some of the packages that you'll see that use some of these. Twisted is probably the oldest and possibly the best known. Stackless, which is, God, it must be 10 years old now. Eventlet, which came out a couple of years ago, which used the Greenlets, which were from Stacklet. Gevent, which is it's my favorite. It's a wrapper around the Greenlets. So it takes care of a lot of the ugly parts for you. It's getting to be used more and more. Spotify has put some funding into it for the guy who writes it. In fact, the whole Spotify infrastructure is run on Gevent and Python. Concurrence, which is an older model of it. I know some people that still use it. I would not suggest even looking at it. And how do they work? What they do is they monkey patch the I/O functions and make everything non-blocking. Not everybody does it for the file descriptors on the disk. We don't have a package which says, hey, I want to read something from a disk, and I want to make it automatically non-blocking I/O. Unfortunately, that doesn't exist. But where are you going to get most of your blocking, since we went through what things cost? It's going to be when you have sockets. Network latency is where the most blocking is going to come in. But all of these have an event loop that listens for IOs on eligible events. It might be a poll, it might be a select, it might be libevent, it might be libev. And we talked a little bit about preemptive scheduling. On a multi-level feedback queue, you can say, I have 1, 2, and 3 for priorities. I always want to execute 1 first. So I'm going to preempt, even though this guy's next in the stack, I have one which is scheduled as 1, I'm going to put it up. Now that sounds like it makes a lot of sense. You can run into problems with it. You can, if you start doing it, actually we talked about how we would do this in Python if we did it for the GIL. And it gets to be really difficult because what happens if all the 1s go up and the 2 and the 3 starve? You get a lot of 1s that are coming up. And then there's a thing called priority inversion that you can run into where things end up starving also. So none of these at the moment have solved the problem of how to put in priority scheduling, so they're all basically first in, first out, bang, bang, bang. It's a stack. Asynchronous callbacks, some of them use. When this event occurs, here's a callback of what I want to happen. and they will vary by how much you actually have to program yourself. How many people have used Tornado? Oh, I thought it would have been larger. Tornado requires you to describe how that's going to work. So there's a main loop that services all the coroutines as a FIFO basis. As I told you, if a CPU-bound process goes in, you're toast. It's just going to block. The ones that probably, they all use this model, whether it's called the reactor or the several other names. The names that people give to programming paradigms just absolutely amaze me. What you need to know is it's a FIFO queue, and forget what the technical word is for it. And there is no migration of coroutines across tasks, okay? So how's this all going to look in the real world? What does it really do for you? Well, we come to the world of Nicolas Piel. It's about 1.5 years old now. Nicolas, if I go over to here, took a bunch of the packages and ran really detailed tests of them on web servers. I've been exchanging emails with him over the past couple of months. I'm trying to get a company in New York to give me the infrastructure to run these tests again, because some of these have changed, but with very, very few exceptions, which I'll note, this will show you how one package compares to the other. So the first one is an error rate on a server. And I've highlighted G Unicorn, Tornado, Twisted, and, oh, that's right, Gevent wasn't in this one. So lower is better. Look at the error rate on that. That's Twisted's error rate. And once you get down here, you're getting Tornado and G Unicorn. That's a pretty enormous difference between slightly above 0 and going up towards 200. Now, also, too, if anybody is using Chrome, this is really cool. If you have the latest version of Chrome and you say, save a web page, I have no network access for this. It saves the web page and all the attachments and everything that's on the website associated with it, so you can run it as a standalone without any network access. Now, here's the success reply rate. So obviously, larger is better. Gevent comes out way at the top. There's Twisted. Okay. I'm only using these because Twisted is probably the most frequently used framework that I've seen people use. So again, Gevent and Twisted. Response time. Less is always better in response time. Who's at the top for the worst response time? And down here, Gevent, once you get beyond 8,000 connections, it gets a little bit up and you can barely see it. Okay. Now, the error rate. This is under HTTP 1. The error rate before was on HTTP 1.0. I don't think anybody uses 1.0 anymore. But, okay, so less is obviously better on an error rate. Yeah. And ModWhiskey, which is a really interesting one, and Tornado and Gevent down there, but you can't even see the difference of them because they're both basically flat. Now, memory usage is something else. Memory has become very, very cheap, so it's not the problem that it once was, right? However, memory isn't free, and I don't mean just buying it, because when you have context switches and you have non-contiguous memory, there is a cost where you have to consolidate. If you have to read something from non-contiguous memory, how many places are you going to have to go? Yes, that's faster than a disk seek, but still, just because it's in memory doesn't mean it's faster. One of the things Google does to make their response so quick is there are ongoing processes in Bigtable which, in effect, basically keep everything contiguous all the time. And they keep track, when they write to a disk, they keep track of where the first block is of that. So when you go to look for a file, it doesn't have to do a disk seek. It knows it's on this machine, on this disk, on this sector, so it's an O of 1 to start reading the file and reads it as a 64 megabyte block. And that goes into memory, and since it's already contiguous on disk, when it's read into memory, it's just one disk read, and everything is already contiguous in memory when you move it up. So, think about this. Not too bad. You know, Gevent and G Unicorn is based upon Gevent. You can see these guys really have probably the smallest ones. Yeah, this one here, Whiskey Ref, I have no idea even what that is. I've never run into anybody that's actually used it. So I think that's the end of Nicholas. And you can go to his website. It's in here. It's really, really interesting to watch. Oh, and also too, it's non-Python, but try using Nginx as a reverse proxy in front of all this. And what does Nginx use underneath to get the speed that's so remarkable? It uses coroutines. Except they have a C version of coroutines. Everything that we've talked about so far is exactly what Nginx does, and in fact it has the same scheduler. But if you have used it before, it's good as a web server, but as a reverse proxy, it's absolutely amazing. So these are some of the updates on Nicola. Tornado, if you look at it, it had a problem with a bisection algorithm, so you get a spike sometime, and they have cleared that. The low results of Gunicorn, and I had to look this up. How many people deal with TCP cork on a regular basis? Good, I'm not the only one. I didn't even know what TCP cork was. I had to look it up. It has to do with Nagel's algorithm, which if you really want to get down to start optimizing things, which is beyond the scope of this talk, it's how TCP was a problem in the early 80s, and the algorithm still tries to help you out. It works great for Telnet, but it's a problem for other things. But look up that, and also how the slow start algorithm works to form congestion windows for TCP. One of the things people do to try to get better performance is just to have an open socket. And they say, oh, well, I don't have the Synax SYN, I've gotten rid of all this cost, I'll just keep it open. But the slow start algorithm for the congestion window in TCP is very aggressive about resetting itself. So since you already have it open, it will reset the congestion window for you, and you have to go through it again just like you've set it up. So you've only saved that much of the setup. The thundering herd. This comes about, there's a paper called the C10K problem, which is a number of years old now, but still quite relevant. What happens if you have your startup? You're struggling for months, and then you put out your product, and it's so successful that everybody loves it that they come in a thundering herd, and your servers crash. That's everybody's nightmare, because then everybody thinks you're a loser, and they don't want to come back. Seriously, it's like the worst thing that can happen to you. Actually, let's talk about that for a second. I put together an Echo server, and I put it on a closed network. It was two of my computers going through a hub, so there was no external network. And the reason I use that is you're saying, okay, I have to open a TCP connection. I have to go to the other side. It has to receive the data, turn around, and bring it back. So there's nothing external that's going to look at your return and error rate. And I wrote the server with Gevent, and you'll see how simple it is to do it. But I wrote the client in Go, because I just couldn't get the throughput that I needed with Gevent. Go has this thing called Coroutines, and they're only 4K to instantiate. And it happens to be very quick. That's where Go really shines, is for this type of multiprocessing. So I was able to, I was setting up a client which says, okay, open 20,000 connections, but don't do anything with them yet, and then send data as fast as the kernel can possibly send it to it. So you're hammering the server literally with 20,000 constant connections going through. And you saw what the error rates were for Twisted and some other things, and how many packets were dropped, etc. So the other thing to remember is not every server is an HTTP server, though it's what most people do. I have finished a project actually for a client where it's kind of service-oriented, but Gevent makes writing your own little server so efficient that you can run a separate server on individual sockets with a footprint that's that large, and you have a table that knows where to call, so you don't have to go through Apache putting up a bunch of threads and having all the overhead of HTTP. You can write a server yourself that does an orthogonal function. And that's something to think about, because that can do enormous things for your scaling. If I have 20 possible things that can occur when I send a packet, and I have to go through Apache, and I have to go through an application server, what if I just send it to this one internal socket? It knows what to do. It either rejects it or gives me back a response, and I don't have any other contention on that, either for threads or processes that are already set up, or on the TCP socket itself. So let's take a look at the numbers and see what that does for us. Where are my numbers? Here are my numbers. Control J, window. And then we will go back and look, now that we know more, what happened with the big files. Okay, great. Okay. I guess that's going to be the best we do. I need just to see the legend, and this is with 20,000 open connections. Well, I just have to memorize, it's min, max, mean, standard deviation. Okay? So I open 20,000 connections, and then I have a variable for the number of repetitions. So I have 20,000 connections, and I want each one of them to send 20,000 requests and back. Now, these are the time that it took with the Gevent server, and you pretty much want to look at it so that you can see what happens. Suddenly, the max gets very big when it gets around 20 million, or 2 million. But then, it kind of averages out after that. And I mean, we're talking about, what, 40 million round trips here? So that's, well, actually it's 40 million requests, so that's 80 million round trips. And suddenly you reach this point where everything is, pretty flat, and the standard deviation isn't that large. You'll see that. So what you're getting is a very consistent response from a server that you've written yourself, and in all of this, I didn't drop a single packet. So my error rate was 0. Now that we know how these work, let's go back. Could any of that have helped with the big file processing? And as someone said, coroutines, okay. So we talked about splitting stuff up. We've gone through that. Gevent, that's not that interesting. Okay, here it is, the composite that we were talking about. This is, I took from all the different ways, and you can go back and look at the code of how you could possibly process the file, pipelines, chunks, threads. We haven't touched on futures yet. I can't remember if I had to take the slides out, but I'll talk. Futures is something that was added in Python 3, which comes from Java. It's in the concurrent.futures package, and a future is a type of asynchronous processing saying, I'm making a request, and I promise into the future at some point to fulfill this for you. Usually it's very quickly done. And you can use pools for it, pools of both multi-threading and threads, and you set up an executor, and you can send a bunch of things to it. It's not quite as fast as Gevent, but it's part of the language, it's incredibly efficient. So here we are. This is the best of all the best times of each one of these algorithms in parts. Let's move it across. You can see, this is the part that was really surprising. As soon as I started breaking the file up into chunks and putting it into parallel, it got worse. And again, remember, I'm not using a database, so there's not that much blocking. The DMAs on modern PCs are relatively efficient. So the system time, in this particular case, for the context switches, overrode what I was going to gain by dividing it up into pieces and putting it into individual processes. So this is what I said, that how to get good response by parallelism and concurrency and not knowing when to do it. When we were at the Echo server, we're using Gevent, which is exactly what we were talking about. Little pieces running at the same time, switching back and forth, and we were getting amazing performance and no dropped error rate. But if I do it on a file, it's pretty bad. However, that being said, if you pick the right way of doing it, this is the, this is the difference. A 52% difference in time. If I use futures under Python 2 and cut the file into chunks, that's the absolute worst time I had out of the best within the sections. So actually breaking it up and using futures in a pool didn't do much good. But when we put it into a pipeline with the coroutines, Python was so efficient, it was literally 50% faster. So don't always parallelize something. However, if it were a socket, which has that big overhead on it, I tried doing it with threads, which I don't even have here, and once you get past like 1,000 threads in Python, just to start up the threads, you can go out and have children and come back before it's instantiated all the threads. Plus, it uses up so much memory, and it was just like, what, this isn't even worthwhile putting in. And then multiprocessing, I've got 4 processors, I could maybe drive it up to 8 to try to drive the processors, and it just wasn't worth it. So what I got was a thundering herd of 40 million requests coming in with not a single one dropped, and the average time was, I think, the worst average was like 1.1 second, which isn't instantaneous, but if you've got a website that's being pounded, it's still pretty good. Now, let's go to the Echo Server Go, and you'll see what little code was required to write that. Echoes.
So in your comparison, the brute force was actually among the lowest, the fastest.
Of all of them, not the fastest, no. It would be somewhere slightly above the middle.
Okay.
So, let's see, okay, let's go F2. And how are we doing for time? Oh, good. Okay, so we're saying here, this is how we write a server. Okay? Like I said, Denise Bilecko, who writes Gevent, has done a really nice job. Because here you're saying, Gevent server, import a stream server. And a stream server is anything that will take in a stream. Okay? So, I listed on port 220. This is how you set up the server. That's it. You set up a server. Okay? And I've passed it, obviously, an address and a port, and echo is the procedure that I want to execute, because I decided to write this as a service-oriented one. So, here we go. So I pass it a socket and an address. That's really complicated. So, and I'm using socket.makefile here, which allows me to use read line so I can read things as if I'm reading a regular file. I set up a loop saying, while true, read in a line that's coming in over the socket. If it's not a line, break out of here. If it is, strip it and put it to lower to see if I'm getting the signal to quit. And if it is, all right. And that's something you always want to do before you close, because you want to flush a socket. Because if you close it down and there's still stuff in the buffer, there's no guarantee that it's going to be written through. So you always want to flush your buffer. Otherwise, I actually have something. And I put this code in for debugging because in the, it was a sanity check. In the large file, the first field in the large file is a line number. So I wanted to make myself feel good that I was actually processing all the line numbers of things that came in. And it turned out to be, that's how I knew I was not dropping anything. And so you write back your act. This is it. I mean, look at that. You write the line, you flush the buffer. You now have a server that you could put any code in here. You don't have to use RPC. You're just calling for it, bang, and you can get it back. And this is the server that would serve 20,000 simultaneous connections. And that's what it took to write it. So I think we're getting, and this, oh yeah, this is what it looks like. Pretty much this is the CPU usage that was required by the server when I was pounding it. The memory, once you set it up with the connections open, it's a flat line across. It efficiently swaps things from the heap to the stack, so you don't have any memory problems. Obviously, this is high because this is the traffic, but this is the interesting part. This was, look at that. You don't see any peaks and valleys in it, really. This is incredibly efficient for handling it coming in because you're not doing the context switch, you're not doing mode switches. It just takes it and goes on its way. So when you start seeing things like this, now, if you wanted to get really fancy, what if you had, the 4 processes and you were running a separate server on each process? Then, if your CPU for all 4 of them was still up here, this is on a laptop. Think about that too. That's what also, I forgot. I'm on a laptop. I'm running 20,000 connections through a network at the same time on a laptop. If you have a real machine, think about what you would be able to do. So the G advantage is you don't need to write asynchronous code like Tornado or Twisted. I've used Twisted for 2 projects, and it does some things really quite well, and I'm amazed by what the guys did. But if I walk away from the code, even though I've commented it for 2 months, I come back, I have no idea of what's going on. And I felt better. I thought, am I the only one? And Guido mentioned this last year in his plenary address. He said, I can't use stuff like Twisted. I can't wrap my mind around it. If Guido has trouble wrapping his mind around it. So it's just, why? The other question is, why should you as a programmer have to tell the machine how to do asynchronous processing? Why shouldn't that be abstracted for you? And I think it should. So I don't even look at Twisted or Tornado anymore. It's just because the code itself is so difficult to go back and understand, or if someone else has done it. They did a study. Code is read 85% of the time and only executed between 10 and 12% of the time. The rest of the time it's either being stored or something else. So 85% of the time is actually reading code. Gevent has the memory and CPU usage are consistent and extremely small. The behavior is consistent. And the new version, you have to go to GitHub to get the beta version. It uses libev. It's also what Zed Shah used from Mongrel 2, did a whole bunch of tests of saturating his server, and he came up with the same thing, that libev is that much faster. And Gevent is the only one that wraps coroutines now and uses libev. So, this is the next one. We'll show how to write a Gevent crawler and also one with futures where you want to go out and collect information from data sites and bring it down. But since we're coming up on, we're past 11 o'clock, so we will take a 10-minute bathroom drink, whatever you, actually don't even tell me what you do, just take your break. And we'll come back here in 10 minutes at 11:15. Because my cord length is stretching at the moment.
Oh, okay.
I have absolutely no. Actually, let me,
I was just thinking of rotating it slightly.
so like this will make it easier for you to see? If I pull it like this?
A little bit.
Why don't you, somebody get up on that side, since you made the suggestion.
Okay.
And I'll just try.
Oh, the other way.
Oh, the other way.
Other way, yeah.
Okay, no, we've just reached cord length.
Okay.
Okay. Ooh, now I'm on the stairs.
If
No, it's okay.
Problem,
No, I want to make sure people can see this. What's the point of it? Hey, look at the screen. No, I can't see it. Okay. Okay, here. Here is if you ever want to open like a whole bunch of threads in Python and see what it does. I've already done the code for you. I would suggest taking another window and running something like top or the system monitor, and you'll see what happens. And the interesting thing to watch it on top is when Python allocates for threads, there's a lot of unallocated memory. It's like, I know I'm going to need this, so that if you ever made these active all at the same time, which is what the thundering herd is, which is why I couldn't use it, you would probably force your system to reboot or something because you'd run out of swap space. But, as I said, if you've got the spare time and you really want to amuse yourself. Okay. Now we're going to talk about, that should actually be, that's slide 85, and that should be 40 URLs. It's actually 40 URLs. So, I said, one of the things you sometimes have to do is you have to go out and get a bunch of stuff from websites, pull it down, maybe do something with it. It's effect like a crawler. I wrote a system like that, and just to see what would happen, it was one of these Sun machines with 60 cores on it. So I ran multiprocessing on, I forgot, I had 92 multiprocessing instances. In each one of those, there was a twisted instance. And I did it late at night, and it was a test machine. But apparently I set off an alarm because I caused the CPU to flatline at 100% for like 20 minutes. But what I could get from it was I got somewhere between 48 and 56,000 URLs per minute that I was able to download. And that was with Twisted, and we saw how Twisted doesn't scale as well as the other ones. But here's one, a Gevent URL client. Yeah, let's get rid of that one. We've seen enough of that. That's the futures. Well, we can talk about that one first. Futures. We talked about you can get futures you make a request and you go out and promise. Now, futures are part of Python, and the best way to use them is they have a pool option. This is something you're going to run into virtually all of these. It's better to have a pool. Because remember we talked about forking something is very expensive? Get a pool of things that are available, and then let someone else mediate, saying, oh, I have a worker here that's not doing much, let me assign it, and you save the startup costs. With futures, you can either have a thread pool or a multiprocessing pool. And actually, depending upon what you do, you'll find that one sometimes is better than another. There's not a clear guideline which is better to use. Except, if you're using Python 3, don't use multiprocessing pools, because I discovered a bug in it. And actually, it was interesting. I had dinner with Guido and Jesse Noller last night, and I somehow got brought up. And we pinpointed probably where it's happening, and it is a problem in the multiprocessing module. So don't use futures with multiprocessing if you're going to do any sort of load in 3 at the moment. So here we go. Futures are really cool, particularly if you're using smaller batches of things. They're incredibly efficient, so that if you have a bunch of deterministic processes that have to run along and they're small, this is a great way to start out if you don't want to go towards Gevent. So let's take a look at it. It also is part of the standard language, because sometimes you're working at a place where they don't want to have a dependency on a third-party library, as we were talking about at the beginning. For example, Gevent right now only runs with Python 2 series, 2.5 and above. There were plans to move it to 3 at one point, but the poor guy is working on it himself, and he's getting money from other companies. So if somebody has a company that really feels compelled to do this, let me know, and we'll make sure that he gets some money. So here we go. Let's look at this line right here. They're both the same. It's just a difference between thread, a pool, executor. They have what are called executors. And you don't even have to worry what they are. You just say, create a pool with these executors, and then I'm going to submit jobs to it. So let's bring the screen across a little bit. Actually, let me do this. Maybe that will make it a little bit easier. So you're creating, what I'm saying is I have a list of URLs, 40 of them, and I want you to go out and pull as much as you can from them. And what I did is for the very large test, I said, take this list of 40 and then make it into a larger list. Maybe make it 10 times as large. It's still the same 40, but you're going to be going through, because I couldn't come up with 4,000 URLs. I probably could, but I had other things to do. So you submit it to an executor, just like you would with threaders and multiprocessing. Here's the name of what you want it to execute, and here are all the arguments, and how long you want to let that future try to execute something. Because what happens if you're going out and something just starts to hang? You want it at one point. This is probably one of the hardest things in design to come up with. How long do I let something run before I say it's too long and let it die? And there are no clear guidelines on that. You have to know your environment, and you have to know what your expectations are. Log status, because I log everything. And what kind of expression am I using to build this? You can see I'm putting it all together, and it gets loaded in. So we've got a comprehension here, and that gets loaded into a dictionary, so that the key of the dictionary is the future object itself, and the value is the URL. So I start all this stuff up, and once I've got it running, I then just have to increment through the futures. I'll say, as they are completed, and it will do its own checking. It will say, as soon as somebody in the dictionary is complete, because we know a dictionary is actually a hash table underneath. And what is the time complexity for retrieving something from a dictionary? 1. Okay? So it can keep going through these things, and it becomes a linear time if it has to go through. Is this guy completed? Is this guy completed? It's very much like libevent and libev. And as they're completed, I just had future to URL, and I pulled out with the key, because remember, the key is the actual future object itself, the URL, and I printed it out. You could also have it where you say you have future result, where you send it off, and maybe it does some calculations and gives you back a Fibonacci number for all we know. And you could say, get the result from there. But the really neat part is that this is the whole loop, and it knows when things are completed, and you can iterate through it. So you've created a series of future events through which you can iterate. And it's all part of the language, and they are actually quite fast. If we can, let's see, go to URL client. Okay. So these were, Control J. Now this was kind of interesting. So I put together the pools part of threads in Python 3, threads in Python 2. These are all futures, future pools, and multiprocessing in Python 2, because 3 is broken. So these are the number of workers that I put in the pool on the bottom, and this is the number of seconds it took to get 2,000 URLs.
Sorry, what's the green line?
the green lines. The green is, I think, multiprocessing itself. Let's see. It's Gevent, sorry. So, if you're using one, they're all basically the same because they're bound by the blocking on the socket. You know, a huge one down here. But once you get down to here, 9. I stopped putting multiprocessing in after 8 because I only have 4 cores on my machine, and you can see that multiprocessing, you know, running 12 processes on 4 cores is going to become counterproductive. So by the time that you get to 9, it's pretty much flat going across. But you can see the Gevent again is the clear winner in it. So you get much better performance from the Gevent. But the important point to take from this is increasing your pools beyond a certain size is not going to help with performance. In fact, you can see there's just a slight uptick once you get past 16, because that comes into the dreaded bookkeeping effect. Because when you start parallelizing things, you have to think, what is the bookkeeping involved? And we'll talk about, Joe Armstrong from one of the inventors of Erlang talked about that a lot and how he deals with it for SMP, symmetric multiprocessing. So the Gevent URL client is very similar. We can just take a quick look at that. URL client, Gevent pool. Okay. Nope, wrong one. Actually, since we're running a little short on time, it's just to look at the code. It's the exact same algorithm of what you saw before, and as you can see, the times are good. So, Gevent synchronization. Gevent has synchronized queues. That's what we talked about before that Python has also. That an easy way to communicate between your individual processes is by using a queue. You have a consumer producer, you have a process over here that consumes it, and you usually have multiple producers. You can use queues as channels. This is really interesting. If you say that the size of the channel is 1, of the queue is 1, it becomes a channel. Now, what is a channel? The channel comes from the concept of a paper from 1978 by Tony Hoare, the man who brought us quicksort. It's also interesting, like Bertrand Russell, he started off as a philosopher, became a mathematician, but then he moved into computer programming. Communicating sequential processes was an idea that he came up with in 1978, and then slightly modified in 1984, and it's this idea that's been lying around for a long period of time, and it's kind of like a pipe, and no one's really implemented it. This is where I'll talk a little bit about Go, that if you have to scale to the next level. Rob Pike and Russ Cox, who are working on it, have been working on that for years, and they know Tony Hoare, and they've gotten channels to work extremely well, and Gevent is starting to try to do the same thing. It means that if you have 2 processes, if you send something down, I have a channel in between. Unlike a pipe in Unix, it doesn't have to look at it at the system level, it looks at it at the Gevent level. And if I send something down this channel, it blocks until somebody is ready to consume it on the other side. And is bidirectional, one at a time, but it can be bidirectional. And you can send different things down it. You're not, right now I think that you are limited, like you are in multiprocessing, by what Python can actually pickle. And that would mean you can't send file handles, for example. Python can't pickle file handles. But the interesting part of that is if you start rethinking the way that you're doing certain things, you can get rid of a lot of mutexes and locks, because you're saying, okay, I'm not blocking. You do your actual blocking and mutexing by sending down the channel and communicating more and more, and you never use shared memory for any of it. And that in itself is a topic, you know, of a 2-hour discussion, but I would encourage you to read some of Tony Hoare's paper. It is kind of sort of discrete mathematics heavy, but it's a fascinating concept, and it gives you a whole way of not working with threads, which, oh, this is what I didn't talk about. How come coroutines didn't take off and threads suddenly took over? What happened? We were talking about Dijkstra and the Dining Philosophers. I didn't finish it. Why did threads, which is not a great design principle, suddenly take over? Truth is, nobody knows. It isn't. It's like, suddenly somebody came up with this idea. It's like they had forgotten about coroutines, and then threads, and then you got this whole idea of mutexes, and then Java came along, and Java put in threads. And I think we sometimes forget, being Python programs, what a big deal Java was when it came in, because in the early 90s, C++ came out, and everybody started pulling their hair out when they saw templates and how bizarre the language was. In fact, Bjarne Stroustrup showed it to Ken Thompson at Bell Labs. He said, "What do you think of it?" He says, "It's terrible." And he refused to speak to him ever again. So C++, if you use a small part of it, it has a lot of nice things in it. But oh my God, the STL and Boost can just be so complicated. So Java came along, and it put in threads too, because pthreads had been written a couple of years before that. And then Java so dominated the market, and we also forget that was a language that was written to control our toasters and refrigerators. That was supposed to be an embedded language. It wasn't supposed to be for web devices. So threads suddenly became entrenched, and then everybody that went to school learned about Java, so they learned threads. So everybody said, threads, there's got to be more threads. So coroutines got lost, and now people are saying, wow, we have started to scale. Well, people like Facebook and Google coming on, we started to scale to such a large level. Guess what? Our operating system, which was written for single core processors, and we've kind of adapted it, and in 2.6, we started sharding the kernel to try to keep track of it, but it still has context switches, which is the single largest cost you have to watch out for. So suddenly said, hey, remember that thing from 1958, coroutines? So they're starting to write it, and all of them work the same way now. Is it perfect? I have the discussion with Peter Portante all the time. Is it the best way? No, but do we want to wait around like multics till somebody finds the perfect decision? And this seems to be a pretty good way of doing things, but I would suggest start looking at queues and channels and try to think not using mutexes. It does have events like you have in Python. I would suggest not using them because just like in Python, if you aren't super careful with your program, you can actually miss events and you don't know what's going on. I would stay away from that completely. Use queues and don't use the events. It has coarse locking primitives, and that's what I'm saying. You should try to avoid locking. Now, we'll talk about a little bit about libevent versus libev because it is such a huge thing. These are the actual dates that I referred to before. November must be a great time. It's like I got a release before Thanksgiving. This is so superior. If you have any of these and you're doing a design, you want to use something that we haven't talked about today, check to see which of the two it uses. If it doesn't use this, look for something that does. This is the future. Design. Okay. These are just some design points to think about because I just taught a class on how to solve problems as a generic way. And the first point I make is really understand the problem. I mean, really understand. I had a simple problem about how you use X number of bricks of 2 different lengths, and can you make a line of bricks this long? You have to write a procedure from it. And it was interesting because I asked after about 5 minutes discussing about it, can somebody restate the problem? And it was like watching Kurosawa's Rashomon, where different people see the same event and describe it a different way. They all described the problem differently, and 3 out of the 5 people were solving a problem different from what I had described. Though my favorite one was, there were 5-inch bricks and 1-inch bricks, and someone said, do we have to account for floating point? I said, I don't even know how to answer that question. But first of all, design is probably where you want to spend most of your time, and I don't think most programmers spend enough time there. It's like, oh, let's sit down and hack. Let's start writing, and I'll see what happens. But understand the problem. First question is, can you decompose your data? Can you break it up into chunks, which again are orthogonal, that you could parse out in different ways? That's particularly if you're dealing with big data that's unstructured, that's something you really want to look at. And divide deterministic from non-deterministic functions. But somebody describe the difference between a deterministic and a non-deterministic function, which is a weird way because a function should be deterministic. Go ahead.
Non-deterministic functions have external influences which cause them to produce different results given the same input depending on when or how you call them.
Right. And that's generally not good unless you're looking for random numbers. Right? But as you remember from, I think it's an algebra, where they talk about a function is like a black box. You put in x and you get back y. There are some parts in the real world that are not algebraic. So determine what they are, divide them up, and separate their processing out. Because if you have them mixed together, not only are you going to be changing state, it makes it much harder to debug. Can the deterministic processes run in parallel? Sometimes they can, sometimes they can't, because even though they're deterministic, I might need the result from something before I can go on to the next one. Any of the processes concurrent, and we remember what concurrent means. It's not just parallel. It means that if I'm going down here, before I decide how to finish, I need to know what this guy has arrived at this point. One of the projects I'm thinking about, if I ever have time, is if anybody has done k-means clustering with unstructured data. Right now, it's a big iterative process, but wouldn't it be interesting if you pick certain centroids and you went out and then probabilistically, when you're, say, 50% of the way through, you can figure, is this going to be a good cluster? Tell the other ones about it or tell a scheduler and not even bother to finish that. And you could start taking large unstructured data and processing it far, far more quickly. If anybody's interested, come and talk to me about it. I just haven't had time to start on it. Does it lend itself to MapReduce? MapReduce is an idea that had been around in individual pieces for a long time, particularly in Smalltalk. And then Jeff Dean and Sanjay Gemawat from Google. And Jeff Dean is the guy that, when they were thinking of using Oracle as their database in like '98, said, give me 8 weeks, I'll see if I can come up with something that's usable. And he basically came up with a workable version of Bigtable in 6 weeks. So once they had Bigtable together, he and Sanjay Gemawat sat down, and they were thinking about map and reduce. They said, well, if we could combine them, and they came up with the whole concept of MapReduce. And now it's available in I don't know how many different ways. Hadoop is probably the most frequent way that people use things because it's open source. But MapReduce is not always, again, it sounds like it's a panacea. Be careful and calculate what your costs are going to be. Now, this is probably the most important. Separate out your I/O and CPU-bound processes. Remember how we talked about making little servers that are orthogonal? I talked about this in the break. If you have something which is very I/O bound and then you come to something which is CPU intensive, even if you're using Gevent, it's going to toast you. If you can separate that out, let's say that you have the money to buy 2 servers. One has SSDs on it and has the fastest bus, and the one over here is the special one for CPU. You have the fastest CPUs on it. You could make a call out to that to prevent the rest of your I/O stack from being toasted and then have it come back. And if you're really cool about it, you could do it on a channel. Okay, and that will block until it comes back and move it out. So something to think about so that you communicate as opposed to doing sequential execution. Because even if it looks non-sequential in your code, remember the operating system always is sequential. Do you need a separate coroutine for each process, or can they run in a pool? Generally, a pool is going to be better unless you're dealing with very small numbers. I tried it just to see what would happen if I create like a separate coroutine for 40,000 connections. You can get it to work, but it's a dope slap. But figure out how big your pool needs to be, particularly if you have something like GUnicorn, where you can adjust the size of the pool. The number of workers that you're going to have is going to be a big predictor of how good your performance is going to be. And it's going to vary depending upon your traffic. And that's another thing to do is analysis. You want to measure, test, and then measure again. So let's say that you have a pool that works really well, but then between 3 and 5 in the afternoon it doesn't, because people are going home and they're checking your website to see what they can do that night. So another thing to do is to program in the ability to have pools that shrink and grow and have them do a deterministic, or I should say probabilistic, computation based upon characteristics of your network traffic. Sounds a little complicated, but it can pay off in spades if you have a very busy website. And a question you need to ask yourself is, how fast is fast enough? Seriously. I wrote a quasi-real-time distribution system for a big financial institution on Wall Street. And they wanted to do it in Java, because we know Java is good in Java. So I said, there are problems with it. I said, you probably want to do it in C if you want it really fast. And I said, I tried it in Java, and it didn't work, because the way garbage collection in Java works is just it would be fine, and then you'd have this huge spike where nothing would happen, and it would go back down. So I said, before I do it in C, let me prototype it in Python. So I started prototyping in Python using some of what we talked about here today, and guess what? It was fast enough in Python. Because their limit was that there could be 100 millisecond delay between things, and I averaged between 15 and 40 in Python. So we ended up writing a quasi-real-time delivery system using Python and not having to go to C. And that was fast enough for what they needed. You want to make a difference between, is it a website or is it a heart monitor? You know, 50 milliseconds may not make a difference on your website. However, if you're looking at somebody's heartbeat and it's skipping every 50 milliseconds, there could be a problem. But seriously, think about what is fast enough for you. And think about, is Python the right choice? You don't want to become like the Java guys. Think about it, is it the right one, or is it, and remember, you don't have to use just one language for the entire project. You can mix and match them, and I would highly encourage people to at least feel comfortable with 2 or 3 languages. Embrace eventual consistency. What is eventual consistency? There must be some database people here. Mr. Generator.
Don't worry too much about relational integrity or data integrity until later. You know, right? Focus on access and the ability to do, for example, an insert, even if it may not be consistent yet. Have some background process that cleans it up.
Right. And that's specifically for a relational database. Think about if you just have data, is it being read or written more frequently? Are you calculating real-time trading on it, or are you just providing information on book sales? Does it need to be up to the absolute millisecond, or if it's eventually consistent within a second, is that good enough? This is sort of part of the, is it fast enough? But think about that, because most of the time, if it's a website, you don't need to have immediate consistency. Check your database driver. Oh, I did make, and I was corrected, it's not PyMongo, it's async Mongo that Bitly does. But check your database driver. That's probably the biggest source of bottlenecks in most of the processing that I've seen. And the last one is a term that, actually, when I was more serious about cycling, Lance Armstrong's coach, I went to a clinic by Chris Carmichael. And he said, one of the things you really have to learn as an athlete, and I think it goes for programmers too, is to learn by surrogacy. And by that he meant is see what other people have done. Not just by like their training program or their programming. How did they approach things? How did Guy Steele get to be so smart? I read up on it, and it was interesting that when he was in high school, he didn't understand something, so he took, and this was in the 60s, he took home a manual for 2 of the machines of the summer, and little by little he understood how each instruction worked and led to the next one. There's an interview on the internet with Donald Knuth. And when he was a senior in high school, his vice principal took him aside and said, Donald, you're a good student, but I don't think college is for you. I don't think you'll prosper in that sort of academic environment. And he said, well, I didn't let him get him down, so I applied to school and I went to school, but the first course I had was something I had never even heard of before. I had never heard of calculus. So what he did is he did the homework assignments, which were all the odd-numbered assignments, did the even-numbered assignments, and did all the extra credit assignments in the back at the same time. And he did it simply by repetition building strength. So if someone does something that you've done, like how does Gevent do it? How does Go do it? How does Erlang do it? Learn from their design patterns, not only what they're doing, but how they got there, and that can spark incredible new ideas in what you do yourself. Look at Guido. He invented a language because he didn't like the other ones. So, parallelism will likely help you scale, but it will not necessarily, as we've seen, will not necessarily increase the real-time performance. And that's the other question. Is real-time performance what you're concerned with, or is it systems resources? If it takes me an extra 3 seconds, but it saves me this on systems resources with involuntary context switches, make that decision before you start to write. Understand the bookkeeping involved, which is probably the biggest one. That if you start doing multiprocessing, everybody knows multiprocessing is great, but the bookkeeping to synchronize on the system level, as we see, can just obviate any advantage that you will have. Make it as orthogonal. That's the word for today. Make it orthogonal. Orthogonal. CPU bound. assume that a CPU, and there are rare cases where a CPU-bound process will be forced to give it up by the scheduler, but assume that it won't. It's rare, it does happen, but assume if you have a CPU-bound process, it's not going to give up the kernel until it is complete. So particularly if you're doing, as I said, anything with video rendering that requires that, assume that it's just going to suck all the time up, and know what is I/O-bound and what is CPU-bound before you start to program. An ounce of math can save you a pound of programming. If you know how something works, one of the things I gave in the talk on how to solve problems, I dealt with Pascal's triangle. And like, one of the questions, if you have a huge representation of Pascal's triangle, what is the easiest way to find the fourth member of the 20,000th row? And a lot of them are coming up, you calculate down to the 20,000th row, blah, blah. But if you know that you can find anything in Pascal's triangle by n choose k, which is a mathematical formula, bang. You just have to put in row and position, and you've got a program that is this large to find it, and it doesn't matter what size your data is. And that's simply an example that sometimes the math and knowing how things work, before you even program, you can work it out. Video rendering, we talked about, compression algorithms. Oh yeah, and that was what we talked about. If you really want to get fancy, you can put them on separate machines. This is the CPU machine, this is the I/O machine, just like you would separate, or you used to separate web servers and application servers and database servers on 3-tier. Inter-process communication, we already talked about, that's the other thing. Share memory by communicating, don't communicate by sharing, or you should flunk any code review that's brought in. Learn about channels, use queues. This is mostly stuff for you to look at later. You've got measure, consider measure again, and now other options. This is also part of learning by surrogacy. Go is, for me, it's been an exciting thing to work with. It's a little over 2 years old now. It was started at Google. Ken Thompson and Rob Pike were having lunch, and they said, you know, we've got a lot of Java out here, we've got a lot of this doesn't really work. Python, I really like Python, but it's too slow for some stuff. So I said, you know, we should write our own language. So they went off, and within a couple of weekends, Ken Thompson had 3 compilers that were working for 3 different processors. And Rob, this is the 4th language he's written over the past 30 years, and they pulled Russ Coxon, Ian Lance Taylor, who's one of the major contributors to GCC. So they started putting it together, and they were highly influenced by Tony Hoare's paper. And one of the things they wanted to make was concurrency and parallelism be part of the language and not a design principle. We've gotten more towards that in Python. If you have something in Go and you want to make it parallel, you say Go space name of procedure. That's it. Everything else is taken care of by the runtime. If you want to talk between 2 of them, you put an arrow, and that's the channel, and it's a blocking channel, and you can have buffered channels. That's it. And it takes 4K to instantiate a Go routine, 4K. That's it. So when I put 20,000 of them for the Thundering Herd, it's, on this machine it takes less than 17 seconds to open 20,000 connections. And the scheduler will multiplex Go routines between threads, though it is a little bit slow. That's something they're still working on. So if you have one process or thread that's being overwhelmed, like it's going too slowly, and this guy really needs to do something, they can migrate from one thread to another. That's really, it's slow now because there's a lot of bookkeeping involved, but the concept would be in the future, if you can migrate from one to the other, why not migrate from one machine to another so that distributed computing becomes part of your language and not a design principle. It's strongly typed. It's an imperative language. It's somewhere between C and Python. It takes care of all the horrible pointer stuff in C that you can use to shoot yourself in the foot, but it has things like slices. The underlying array is taken care of, and you treat it just like a slice in Python. So it's a little bit closer to C than it is to Python, but they were highly influenced by those 2 languages. And its goal is, depending upon what conference you go to and how much they're talking, is to make it the standard server-side language for Google. It also takes about 12 lines to write a server in that, too. I have a Go URL client, which is faster than the Gevent version. I also wrote the Echo server in Go. It uses less memory and less CPU than Gevent. And it's really approachable by Python. So it would be something for you to look at and keep in your back pocket. And the CSP, you can look at that. Oh, that's right. Ian just finished a GCC version. The idea is that it also compiles very quickly. That's why when they first did it, it compiled slowly. And the guy said, well, listen, one of the great things about Python is I can iterate so quickly. I can go, bam, and I know what's happening. So you can compile about 130,000 lines of Go code on a laptop like this in about 1.7 seconds. You go make, boom, bang, it's there. And it's statically checked, so there are no runtime errors, etc. You know it right there. It also took from Python. If anybody has ever used C, some programs would have C obfuscation contests to write the worst looking C code that'd be one line, but it would actually compile and execute. They took from Python. There are no semicolons like in the other languages. It uses indentation. And you have something called Go format, which you run before you even compile. And if your indentation isn't correct, it will tell you where it's wrong and try to correct it for you. So it's as clearly readable as any Python code. Yes. But the GCC version that Ian came up with is going to be the optimized version. So right now the compiler, the executables you get are fairly fat with Go. But the GCC version, where you would compile for threads, they want to compile for Go routines. And it's just taking a long time to get it done, but it'll be we'll have all the optimizations that you can get with GCC. Erlang. I have a couple of friends who have started to play around with this. This has been around since the 80s. It was developed for telephone communications. And for many years, this was the place that you look for parallelism and concurrency. Joe Armstrong is still working on it. It's a functional language. It uses the actor model, which Scala, sometimes people think Scala invented that. It's been around since 1970. And the actor model, a little bit like communicating sequential processes, is all about passing messages between different processes and not sharing memory. It's fault tolerant. It has its own execution stack, so if something falls over, it knows how to restart itself. It's being optimized for symmetric multiprocessing. But Joe has said that once he gets beyond 4 processors, the bookkeeping becomes so large that you lose any benefit from it. And even he hasn't been able to cure that yet. The one distraction or detraction that Erlang has is that it looks like Erlang. If you've seen the code, it's not similar to other languages, so it's not like, oh, if I knew Python, C, or Java, I can, sorry. And it's like something they invented for Star Trek. And Haskell, which is one of the most beautiful languages, I mean, from pure language design, it is so beautiful. Simon Peyton-Jones is the primary person behind this, who works for Microsoft Research in England. It's absolutely beautiful. It's a real functional language. Everything is immutable. And it really uses, unlike some of the Clojure, which does a half implementation, not a half, but not a complete implementation of software transaction or transactional memory, depending upon how you see it. Take a look at that on Wikipedia. This is what the guys from PyPy are trying to do now. It's just, it allows you to do transactions in memory and nothing ever collides. You don't have to worry about state. It's probably, I would think, the hardest thing to implement in any language. The other problem with Haskell is, like Erlang, it looks like Haskell. I've spent the time to learn some of it and write it and say, oh, it's so clean, it's so beautiful. But it looks like I had a spasm on my hand at the keyboard. And once I get away from it for a week, I have no idea. Twisted looks so easy compared to this. But it is absolutely a beautiful language. There's a book called, I think, Programmers at Work, I think it's called. And they interview some of the people that I've mentioned here. You should read how the one with Simon Peyton-Jones is just marvelous. Something else also to look at is the JVM flavor. I worked in Java for 5 years. I'm not a huge fan of the language. I don't hate it. But what they did with the JVM is really remarkable. Unladen Swallow tried to learn a lot from it until the project was canceled. It uses a one-to-one thread model. Jython is a VM version of Python. Scala also uses it. It uses the actor model with thread pools, but it uses something which is a little bit like the fork join that Doug Leia came up with that's being put into Java 1.7. It's a type of work stealing that can be used with thread pools. You should look that up, fork/join. It's a fascinating algorithm, but it has problems in the VM still. Java in itself, Clojure, if you're, anybody here a Lisp person or really still program in Lisp? Okay, you got one person in the back. I mean, I love it as a language. It's just, unless you're on Route 128 in Boston, you know, it's like, not many people use it. But Clojure is a really nice implementation of it. And does anybody know of any others that have concurrency and parallelism built in? If you do, come up and talk to me. I'd love to know about what people are doing. And here's what can you do. This is where I try to make you all feel guilty. Taming the GIL. We've got to do it in some way for Python to go forward. We just have to. If you don't understand it, read Dave Beasley's 2 presentations. They are so clear. PyPy, as I said, is trying to implement STM. It's really difficult, and I applaud them. I'm dying to see what happens with it. If you have, as you can see from the pipelining and other things, 3.2.2, it just beats everything except brute force. Brett Slatkin, who used to work for Google on App Engine and spoke at PyCon every year, but this year, because he started his own company, has an open source challenge on how to deal with the GIL, an idea that he had that's on his blog, and he's looking for people to help him. And Python doesn't have a corporate sponsor, the way Java had Sun for years and now has Oracle, C had AT&T Bell Labs. Python is really a community effort. So I would encourage you not necessarily to write the codes or go to the sprints, so that's a good idea, but think about some of what we've done today, because it's not the idea of the super programmer that comes up with one idea, it just doesn't exist. It's somebody sitting around having ideas, getting together. So think about what we have talked about and contribute, even if it's to a mailing list for one of these projects. So we covered a lot of stuff here, and as I said, I had about 30 more slides, and I just had to just pack it down because this is a huge subject. But if there's anything that wasn't clear or you'd like to know more about, just come up to me, ask me questions anytime during the conference. If there's enough interest in one subject and we want to go further and more into detail on it, we can do an open space on it. And you can always email me at that, but definitely check out the bibliography, which has all sorts of things from around the web that people have written about this in different ways. It's absolutely amazing the amount of information that's out there. And that is pretty much it. So if anybody has any questions.
Earlier in the presentation, you mentioned that some of these libraries, such as Gevent, monkey patch the Python I/O. How do you mitigate side effects for that? Do you anticipate many side effects for monkey patching those types, socket and other I/O libraries?
Okay. I have to repeat the questions for the recording. So the question is, how do you mitigate any problems that may occur as the result of monkey patching, which is available in Gevent? And once you monkey patch, you yourself can't do it because you're writing regular Python code, but I haven't seen problems that have occurred from that. I would have expected to have seen a problem when I did a thundering herd against a server. I didn't have a single error. And also, I think a lot of it has to do that it uses libev, which has been tested now for about 5 years, is incredibly solid. And what he's doing is really putting a wrapper around something that's a proven technology. If you're doing it yourself, that's a whole different kettle of fish. Anybody else? Wow, no other questions. Cool. You guys are smart. Oh, Doug has a question.
Can you spend a moment talking about determinism, not necessarily in your code, but in order of execution?
Oh, determinism in order of execution as opposed to in your code. There are some cases where if you write something in a certain sequence, it's not necessarily going to be executed in that sequence, particularly when you have multi-processes running. What if you go to make a call and you, well, I call this guy first, this guy here, but at the operating system level, it's in a buffer and it hasn't finished. I guess what to say about that is that it's really bad. And you have to take it almost on a case-by-case basis, but part of that is that you have to understand how these things work at a lower level. That, I mean, actually that's a very good point. That's something I should add, that because something in your code looks like it's going to execute in this order, it's not guaranteed to execute in that order, which is also, when you have those occasions, that's why you should not rely upon unwinding of the stack, which is the biggest problem. That's why you should have communication through either channels or pipes, so that you're not saying, oh, I assume the stack is going to unwind in this way. That's also why I sometimes have problems with callbacks, because if you have code, which is I'm going to do this and there's a callback, you're assuming this is how it will execute. Instead, have it wait for an event, not an event, have it wait for a message, and only when the message has been received do you go forward. Because that way, even if one is here and one is down there, the physical representation in your code doesn't matter because you've specified that until this is finished, even if you've written stuff here, put it over there. Does that make sense? That gets to be kind of a complicated subject. Yes? No? Are you awake? Hello? Anything else?
Yeah, I have a question about features. I haven't looked at like the documentation in full, but is that something that like in the future do you think might merge with Gevent, like that library of Gevent together?
Good question. Try using them together if you really want to drive your system crazy. I tried that, there's a reason I did not include it. Also, if you ever did that in a code review, you'd probably be fired. I think they are two different ways of approaching the same problem. A future is saying, I want something, and I want you to promise that in the future you will give it to me, but I'm not concerned necessarily in the order in which you give it back to me. It's like, throw it out and give it back. And for a lot of cases, that's fine. With Gevent, I'm multiplexing it, but I also have the ability to communicate in between. So, for example, futures would work well for parallelism if you don't care about the order in which something is returned and you don't have to communicate with another executing process. Gevent will give you executing processes that can communicate. It will give you the parallelism, but it will also, but because of that, there's a little bit more of an overhead in programming you have to do. I'm not sure if that answers your question, but no, I don't see them merging because even though they're similar, they serve two completely different purposes.
Gotcha. So it sounds like Gevent is like a superset of the functionality that futures give you.
Yes, I would say it's like futures. If you need something in the future, you don't want to have to worry about all the other stuff, it's great. But if you need to control it on a lower level of granularity, you're going to have to go to coroutines.
On that topic, I just missed that in the beginning you said something about the futures, which are part of Python 3, right? But,
yes.
But you can backport.
You can backport it.
So, but you say something is not working.
Okay. I'll make that clear. It comes from actually the Java package of concurrent futures. Java was the first one to have it. And I think it's Brian Quinlan that did the futures for 3, and then someone backported it to 2. They both work extremely well. The problem that occurs is that there were changes made to multiprocessing in 3. And if you use the multiprocessing pool under futures of 3, and you get to, I can get up to like 11 million transactions, and then it will freeze. It has a wait PID problem in the C code. So that needs to be, the multiprocessing module in 3 has a bug, so don't use futures multiprocessing pools. In 3. In 2, it works. It's slow. It's slower for the buildup, I mean overall, but at least it doesn't freeze on you. There was somebody, yeah.
Just kind of wondering, what was the difference between like the forest model of CSV versus like actors model? Because it seems kind of similar.
Oh. Talk to me afterwards about it, because that's talking about the actor model and the CSP. It will get really technical, and I think it'll be an extremely limited audience. But I'm glad you asked the question. Anyone else? That's the next talk. That's like, okay, now that you've got all this information, how do you build this big system? And the first thing you want to look at is 0MQ, which really doesn't have anything to do with anything we've talked here, but it's TCP on steroids.
Well, but it lets you do the channel stuff, right? Like
it lets you do channels on a level above this.
Yeah.
So, yes, definitely. Going forward, if you've got all this in your head and you want to start building it out, 0MQ, everybody needs to know about it. I forget, was it Tim Lesher was doing something on building with 0MQ here? But yeah, that is like so cool. It's like, take TCP and put it on steroids. Easy setup, language agnostic, so you can take all this and then you can bring it up to a distributed level. Other questions? Because we're coming to, we have like 3 minutes left. We're actually going to finish early. Okay, well, I thank you all for coming. I hope some of this was interesting or helpful. And be sure to fill out the survey, because I said we're a community process, and we're really trying to do things that you people want to see and figure out what we need to do better. So thank you very much for coming, and fill out the survey.